So who am I? First off, my name is Lary Blume. I'm a professor at Cornell, and I teach economics, and I have an appointment in computer science. And my particular interest is in economic theory, both decision theory, game theory, and general equilibrium theory. It is in the, I think what interests us of that today is kind of the game theory. I'm going to talk about theoretical models that have application to the study of social networks and economic phenomena taking place on social networks and the like. Okay, and of course now on my other computer, everything is working, so we will change this after the break. So I want to begin by talking about a question of why do we need economic theory? Now, I know that for most of you, economic theory was that thing that you studied in your first year, you passed some exams, and then you were done. Okay, and you'd hope never to have to come back to it. But in fact, that's not the way the world works. Most of you are going to go off to be empirical economists. And when you're an empirical economist, you want to make causal claims. You want to undertake a statistical study and conclude at the end of the study that A causes B. And every time you say A causes B, you are in fact making a theoretical claim. You have in mind, or I hope you have in mind, implicitly you do have in mind a model, and you're making a statement within that model. And so there's really no escaping this. So I want to talk for a moment about how this works. So first off, what is a model? There's something out there that we want to study. And a model defines a collection of counterfactual situations. Okay. Actually, one of the situations, of course, might be factual. It might be the world in which we actually live, or a representation of the world in which we actually live. But you also consider in your model variations on that world. And in the statistical frame, or if you think, for example, about supply and demand, and maybe, so let's do the simplest thing. Let's think about supply and demand, and let's think about, say, trying to understand the effects of a tax, right? So how do we do this? Well, we've been doing this since Marshall back in 1890. We draw a supply curve, we draw a demand curve, and then we shift one of these curves in a way that is to take account of the tax, okay? So we might shift the demand curve so that the price the consumer, because the price the consumer has to pay for the good is the market price plus the price, the amount of the tax. And so we shift the demand curve that way. Now, maybe suppose right now the tax rate is 0. That's the real situation. A counterfactual situation might be where the tax rate is 1% or the tax rate is 2%. Okay, and we want to kind of understand how the change in the tax rate is going to change the market price. And so these alternative tax rates that we might consider, these are counterfactual situations. Okay, well, I don't have a lot more to say about supply and demand. There isn't really much more to say about supply and demand, but let's go back to models in general. To begin with, a model is a mental construct, okay? Now, the next thing to understand is that causality is actually a property of the model. Okay, how do we understand causality? We're going to talk about this in a little more detail on the next slide. But the way in which we understand causality is we ask the question, what happens if we move to one of these counterfactual situations? So, for example, to come back to the demand curve that I said we were leaving forever a second ago, when we shift the tax rate, we imagine the hypothetical experiment, the thought experiment of changing the tax rate by, say, increasing it by 1%, and then or raising it to 1% of the market price. And then we look and we see, well, in that new world with that change in the market price, what is the what is the new, with the change in the tax rate, I'm sorry, what is the new market price? Okay. And if that changes, we say, aha, there's a causal relationship between the tax rate and the market price. So here we understand the tax rate to be endogenous, exogenous, something which is set by some government authority. And we understand the market price to be endogenous, determined by the workings of the system. And we watch how the exogenous variables, how changes in the exogenous variables affect changes in the endogenous variables. So this is what we do all the time. Okay. And if we had a different model, not supply and demand, but some other kind of model, then we would posit some other kind of relationship between changes in the tax rate and changes in the market price. And consequently, we would come to different conclusions. Okay, so causality is really a property of the particular model that we are deploying. And consequently, causality is a property of the mind and not really a property of the world. Now, we know, in fact, that things happen in the world, but it is we who are attributing causes to things that happen. And when we're arguing about which model is correct, right? When we look at the economics literature and we see people arguing about, well, this conclusion is really stupid because the instrument was weak or bad or something like that. What people are really saying is that the model that the researcher employed was the wrong model. And you're arguing, therefore, about different mental constructs. Okay, so in a little bit more detail, how does this work? So causal claims are consequences of, and I should, of model manipulations. And we say that A causes B if, but for A, B would not have occurred. Now, a model contains a collection of variables and relationships between them. And as I mentioned just a moment ago, we classify them as either exogenous variables or endogenous variables. Endogenous variables are determined within the system, whereas exogenous variables are set outside. A world, which may be hypothetical, maybe not, is described by the values of the exogenous variables and the endogenous variables that are determined given the exogenous variables, and different values of those variables define different worlds. Okay, so then what do we mean by A causes B? We say that A causes B if changing the value of exogenous A changes the value of endogenous B. Okay, now a model is a structural model if the relationships in the model are stable with respect to the contemplated perturbations. Okay, so I want to say something about that for just a moment. So give me 1 second here. Okay, so first off, the this idea of causation can actually be found in Hume, but its implementation in terms of thinking of perturbations, what I've just described is something called a perturbation theory of causation. This really was first implemented by, among all the philosophers and scientists one could have imagined. This actually was introduced by Alfred Marshall in 1890 in his Principles of Economics. And this is his idea of ceteris paribus analysis, which of course was probably the very first thing you ever learned in economics after the sunk cost fallacy or something like that. This definition of a structural model that I've given is namely a set of relationships that are stable with respect to the perturbations that we want to deploy is due to Jacob Marshak, who published it in a paper in 1953. All the references in my lecture are actually contained in the very last slides at the end. If I've neglected something, you can shoot me an email or grab me during the break, and I can track them down. So Marshak actually introduced this notion of a structural model, and that's the reason why today this definition of structural model is known as the Lucas critique. Now, what does the Lucas critique and macroeconomics have to do with this? Well, if you remember the Lucas critique from first year macro, another thing I suspect that many of you hope to abandon after the end of your first year in graduate school, his idea was that if you looked at the macro models that people were using at the time that Lucas wrote, he said, look, some of the things that are being treated in this model as parametric are in fact determined in equilibrium. Things that are being treated as exogenous are in fact endogenous. And consequently, when we shift some of our policy variables, the relationships that are being fixed by these exogenous parameters are actually changing. In other words, the relationships are not stable. So this is exactly Marshak's idea. And to Lucas's credit, he mentions this. He cites Marshak in that paper. And it's a very short paper, by the way, and I would encourage you to go and read it. And you can find it online at the Cowles Foundation webpage at Yale. So whether or not a given model is a structural model depends upon what we want to ask of it. Depends upon what kinds of perturbations that we're interested in. This is the thing that Marshak actually delineates so well. He points out that, for example, if you are a firm, well, let me actually not do Marshak here. You can read it for yourself. But he points out, he takes a given problem about thinking about price determination, and then he points out that there are different questions that we can ask about price determination that are going to essentially give rise to different structural models. Do we want a partial equilibrium model? Do we want a less partial equilibrium model? So on and so forth. And in fact, probably this is the best example to think about what a structural model might mean. Why is it that we might move from a partial equilibrium model to a general equilibrium model? Well, in a partial equilibrium model, we're holding everything fixed except for the variables that are endogenous to the market that we are interested in, within the market that we are interested in. So if we are studying, for example, the market for coffee, the prices of sugar and tea and everything else are held fixed in a partial equilibrium analysis. But in a general equilibrium analysis, we would let the price of sugar and tea float, and we would understand that there are substitute or complement relationships between these goods. And so, for example, if the price of coffee were to go up, if something were to force the price of coffee up, it might shift some consumption into tea, and therefore the result would be different from the partial equilibrium analysis. So this is an example about thinking about what kinds of perturbations we want to do. Or another example might be, suppose that we want to look at the effect of dropping decreasing the very, very large United States tariff on sugar imports in order to, and we want to study the effect of that on coffee consumption. Well, if we just look at the partial equilibrium model of the sugar market, we're not going to see anything at all about coffee. And so we have to, kind of go to the more general model. So these are examples of the kind of thing that I have in mind. All right, so how does this relate to what we're going to talk about today? How does this relate to social interactions? Well, my point is that every time you are making a causal claim, you are referring, even if only informally, to a structural model. So many of you are going to do research where you say, my model isn't a structural model. I'm doing design-based research. I'm just getting some description of what's going on. And that's good if you're really honest about it. But I have to tell you that I have yet to hear a talk where anybody has really been honest about it. Now, it's not that people are fundamentally dishonest people, or at least that econometricians or applied economists are fundamentally dishonest people, or at least any more dishonest than anybody else. But what's really going on is that when you start talking, you found all these correlations in your descriptive study, and now you're talking about them and trying to interpret them. And at some point, in response to some question, or maybe even without any prompting, you will say, this is a correlation that I really believe in. Whereas maybe this other correlation over here is incidental or accidental. And the moment when you start doing that kind of attribution, you say, this is a real effect. I believe that this is real. You are in fact kind of imposing a structural model to interpret the results that you have. Okay. So one lesson to take away from this is that when you make claims like that, it is a good idea, especially in a job talk, to have thought about the structural model that's going to back up that claim, so that when someone says, well, I think that this is really baloney because something else here is endogenous that you're forgetting about, that you have an answer to that question. And the way that you answer that question is essentially by describing the model that you have in your head. Okay, so whether or not you actually write down equations and do math and all of that, whether you do that or whether you're not doing that and you're just making assertions about your empirical analysis, you are in fact being a theorist as soon as you start making those causal claims. And so what I want to do in today's talk is to show you some rather simple theoretical tools that will allow you to do that in a useful way about social interactions. Okay, so let me move on. Okay, unfortunately, my notes seem to be included in these slides, and I don't know what to do about that. So, well, I do know what to do about it, but I'm not going to take the time to fix it now. All right, so when we talk about social interactions, we are talking about things that are inherently non-economic. Okay, so there is a certain tension between economics and the other social sciences because of our extreme views about, for example, rational choice analysis. Also, our extreme views about what it takes to make a causal claim. Right. Nobody is as religious as economists are about what it takes to deal with problems of endogeneity, for example, in econometric studies. Now, the point of social interactions is that we want to understand that economic phenomena doesn't take place in and of itself in its own hermeneutic, kind of enclosed social system. In fact, that economic analysis or economic phenomena are embedded in larger in a larger social structure. Okay, and the impact of that larger social structure has impact on everything that upon everything that we use in economics in order to undertake our analyses. So, for example, when we're building a game theoretic model or estimating a game theoretic model of some kind of social interaction, some kind of peer effect, for example, in a classroom, or something having to do with the diffusion of technology, in agrarian villages or something like that. When we're building those kinds of models, we take preferences as given, okay? But where do preferences come from? Preferences are not given in some sense. There is a larger framework within which preferences are socially determined. Okay, so our preferences are not entirely socially determined, of course. They come in part from our genes, and maybe in part from our distant family background, but our preferences are also influenced by what our friends are doing, what our enemies are doing. They're influenced by other things that are going on in the world. So in fact, you can think of an economic analysis as a kind of partial equilibrium analysis that sits within a larger social framework within which some of our exogenous variables, for instance, preference orderings, are in fact socially determined. Now, where is this important, really important in economics? If you're studying, so to begin with, if you think about what game theory does, game theory is a model of endogenous preferences. So how does this work? Because I think most people don't think about game theory this way. the way that game theory is a model of endogenous preferences actually works as follows. How do we represent preferences? Well, we say that that everybody who's playing a game has a decision problem, and the states of the world in that decision problem are what everybody else is doing. And then the decision maker has to make a choice from actions available to her. And she has preferences, and these are expected utility preferences, right? So does this sound familiar? This sounds like game theory to you, right? And so when we describe those preferences, these preference orderings, we have two parts to the description. We have a payoff function or a utility function, and then we have beliefs about what other people are doing, okay? And then what does our decision maker do? Given those beliefs, which are represented by a probability distribution over what other people are doing, our decision maker then chooses the action which maximizes her expected payoff. Okay, so how are preferences now endogenously determined? Well, preferences are jointly determined by payoff functions and by beliefs. And beliefs, of course, are determined endogenously by the equilibrium conditions, right? Nash equilibrium is, in fact, an equilibrium condition about beliefs. It says that our beliefs, whatever they might be, satisfy certain consistency properties, namely that our beliefs are correct, okay? That if I really believe that everybody's playing mixed strategies, okay, then if you and I are engaged in a two-person game, then the beliefs that I have about you are exactly the mixed strategy distribution that you're deploying. Now, no one really believes that people actually play mixed strategies. So there is a more subtle interpretation of Nash equilibrium, which talks about beliefs that are consistent with the choices of others. You can find the discussion of this in Roger Meyerson's game theory book. And since this isn't really a game theory lecture, I'm not going to pursue it farther here. But you should know that it is possible, for example, to deploy game theoretic models in, for example, industrial organization settings like price setting for the auto industry without believing that the board of directors of General Motors is actually sitting there flipping coins to choose what prices they're going to charge for cars. But Meyerson is the place to go to read about this. Point is that many of the things that we take as given in conventional economic models are in fact determined by social structure. And so what we want to do is unpack those relationships. Often those relationships or that endogeneity of the economic, the things that we take as given in economic models, sure, they're endogenous, but the workings of that, the causal workings of that, are on a much longer time scale that are really not relevant for a particular subject that we're studying. And so that we can get away with saying that our endogenous preferences are in fact exogenous for our purposes. And this is exactly analogous to saying that sometimes it's okay to do partial equilibrium analysis rather than general equilibrium analysis. On the other hand, of course, sometimes preferences change at a rate on a time scale, which is the same as the time scale of the phenomena that we're studying. There's a large literature in economics on the evolution of social norms. Right. And social norms is exactly this kind of phenomenon. It's changes in the evolution of preferences and of tastes. And if you go into the game theoretic literature, particularly the evolutionary game theory literature, you will find papers which actually talk about not just the evolution of beliefs, which is what any Nash equilibrium model does, but they also actually talk about changes in the payoff functions. Right. So, for example, there are a series of papers that I recommend highly to those of you interested in political economy by Ingela Auger and Jürgen Weibel on the evolution of pro-social preferences. And they talk in this paper in these papers, there's a set of them about Kantian preferences and how they emerge from a kind of game theoretic interaction. They're not changing beliefs now. They're actually changing payoff functions. There's a paper in Econometrica. There's a paper in Games and Economic Behavior. There's another paper in a recently published conference book where you can find a commentary by me on their work, which is actually almost as long as their paper. And I would, so these are examples of how we actually change preferences. Now, there has been, if we want to move away from economics and enrich our economic stories by looking more deeply into social structure, the first thing you might think about is behavioral economics. And I want to tell you that this is a mistake. So I'm not particularly fond of behavioral economics. And the reason why I'm not is that behavioral economics is largely about the economic study of individual behavior. And I am not interested in, I have written papers in decision theory, but I'm really not interested in individual behavior. I'm interested in the behavior of social systems. And when we study social interactions, we are obviously interested in the behavior of social systems. So it's not enough simply to say, what is the psychology of, what a given individual is doing? Instead, we need to talk about how the whole social system works. And this is not largely what behavioral economics does. It is something that behavioral economics could do, and then we would have behavioral social psychological economics, and that would be very interesting. But that's not really yet the agenda of people who go into a lab and look for time inconsistency or look at the effects of a particular nudge or something like that. They're really looking at individual responses and not at the systemic implications of those individual responses. Now, what social science should we turn to for insights into this? My claim is that we have a lot to learn from sociology. And it is surprising to me that there has been relatively little interaction between economics and sociology. Now, one place where you can find a lot of interaction between economics and sociology is actually at the sponsoring organization, one of the sponsoring organizations of this program. You can find it at the HCEO. Because Stephen Durloff has spent a lot of time organizing conferences, bringing together economists and sociologists who find at these conferences that they have a lot to say to each other. So the traditional view, the traditional battle between economics and sociology is summed up in this quotation from that comes from a paper in 1960. Economics is all about how people make choices. Sociology is all about why they don't have any choices to make. We all know what the first sentence is about in that quotation. So what is the second sentence about? The second sentence is about the idea that sociologists, that is attributed to sociologists, they simply say that all choices are essentially socially determined. So individuals are much less free to actually make choices than economists would like to believe. So this is the kind of the fundamental tension between an extremely social view of individual behavior and an economic view of individual behavior. And Duesenberry actually wrote this, and in a comment on a paper that Gary Becker made, wrote it or gave at an NBR conference in 1960 about children's educational choices of parents for children. And Duesenberry here in this he went on to say in the third bullet point, this is another quote from the same thing he went on to say that even though we think all the choices that Gary Becker would have liked to have imagined are free and open to parents, namely, how many children do I want to have 2 children and send them to the best universities, or do I want to have 10 children and tell them to they're on their own after high school? Said, no, you're not really free to do that. There are social constraints that guide our behavior. And the study of social interactions is about tracking those down. All right. So what are the kinds of social interactions that I'm going to talk about? I'm sorry for all of this extra junk. I'm going to, if there is a literature on a rather large literature now on different kinds of social interactions. There are four general kinds of social interactions that that you can find in the literature. First off, there's social learning, right? So some of you have probably read or looked at models of herd behavior. And the herd models are models of social learning. If you're interested, for example, in studying the diffusion of a new technology, that is often a social learning phenomena. There are some beautiful papers, and the authors are slipping my mind at the moment, but they'll come back to me before the end of the talk, on the diffusion of technology for growing pineapples in Ghana. Where the object is to understand how the social networks in Ghanaian villages contributed to people's decisions whether or not to grow pineapples. There's a very old paper, old means written in the 1980s, by an economic historian named Warren Watley, about the diffusion of the tractor in the American South. You can, and he understands it. He didn't have the tools to talk about it this way, but his understanding of this is that it is a social learning process. And he had all this really, really great county level data on tractor usage going back to the 1930s in southern states, and was able to demonstrate how tractor usage diffused from particular farms that were regarded as role models in particular locales, and particular demonstration farms that were set up by the U.S. Department of Agriculture, and how they diffused out geographically away from these centers. And so this is a social learning phenomena. Social norms, I've already talked about. Some of you are probably interested in the economics of education, and one thing that people have spent a lot of time trying to untangle is the effect of peers in the classroom. Now, labor economist, I have a colleague here at Cornell who studies the economics of education, and says that it is really hard to demonstrate the presence of peer effects in the data that we have. And with the models that we use, there is some evidence that peer effects are present in education, but it's not really very strong at all. And so I asked him, so then you're indifferent about where you send your children to school, because you don't think that peers really matter. It doesn't matter who else they're in the classroom with. And of course, his response was, of course not, right? That's ridiculous. So this is not a problem of whether peer effects exist or not. It's a problem of whether we have models that allow us to actually display them and then talk about how they work. Okay. Peer effects are an example of a larger class of models. You might recall from first-year theory the phrase strategic complementarities. And a peer effect is an example of a strategic complementarity. So the idea behind complementarities, basically, so let's think about a game theoretic situation, and you have to choose some action. And let's think, I want to talk about derivatives here. So let's pretend that these actions all are choices that we model as being on the real line. We say that a complementarity is a strategic complementarity is present in this game if an increase in your action increases the marginal utility of my action. Okay, and you might know this idea under a different name. You might have heard the phrase supermodular games. This is kind of the more general framework in which we use to talk about strategic complementarities. So a good example of a strategic complementarity can be found in a paper that is not a peer effect. Direct of the kind that you see in classrooms. So there's a wonderful example of this. There's a paper by a political scientist at UCLA. His name is Suzanne Lohman. Maybe some of you know her work. She wrote a paper called Dynamics of Informational Cascades, the Monday Demonstrations in Leipzig, East Germany, 1989 to 1991. This paper was published in World Politics. And what she actually did in this paper, so some of you, although I know this is ancient history for you guys, for me at least, this was a lifetime event that the kind of the collapse of the Soviet hegemony actually began in East Germany, and it began well, in some sense the spark in the tinderbox were street demonstrations in Leipzig over a period of time that grew in size and scope. And then as more and more people started showing up, demonstrations started taking place in other cities, and you can find many histories of this. And by the way, if you're interested in the history of this, the guy you want to talk to is Durlov, because this is his bread and butter. This is what he does. He's very interested in this stuff. And so, but what Suzanne does is to trace out how the dynamics of these informational cascades work, and the fundamental strategic complementarity is that people who are on the bubble about whether they should participate or not, whether they're just not sure whether they should or not, they're really indifferent in the economic sense about participation. As more and more people turn out, and it seems that people aren't getting arrested and stuff like this, and it looks safer to do, more people join, right? The expected utility of you showing up increases, and therefore you go out, right? And then when you go out and do this, this encourages more people to go out and do this. And we can think of a number of mechanisms through which this might take place, but this is exactly a strategic complementarity. She also has a paper in Games and Economic Behavior that actually kind of lays out a more formal model than you'll find there. Now, papers have been written on social interactions in a number of different areas. They've been written on career choices and retirement and labor economics. There have been papers on fertility, peer effects and social norms around childbearing. There is a lot of stuff in the health economics literature and more generally in the public epidemiological literature on the effect of others on individuals' health decisions. So both with respect to treatments and with respect to what people know about their own health. Certainly, it's hard to understand what is going on today around the issue of vaccination and whether one should get vaccinated or not against the virus without thinking about social structure, right? Education, I've already mentioned, classroom peer effects. There are social interactions play a large role, are very important in thinking about crime. And we're actually going to look at a paper about concerning that in just a moment. There are a variety of different mechanisms out there that make peer effects work. I've already talked about peer effects and role models. I've mentioned them, social norms, social learning. These are all things I've mentioned before. There's something out there called social capital, and nobody actually has a clear definition. That's not what I said is not true. Many people have competing, very clear definitions of what social capital is. But whatever, all these different definitions are in fact social interactions. So, yes, so let's actually talk about in order to see what we can learn from peer effects, let's actually talk about an economic model of crime. This is a paper. I want to talk for a moment about a paper that comes from, published in the QJE in 1996 by Ed Glazer, Bruce Sacerdote, and Jose Schenkman. And this is a very interesting way of, this paper is not just an interesting and important study of social interactions. This is one of the first empirical papers to really get people interested in studying social interactions empirically. But it's also a very interesting way of using economic theory, because they did not use economic theory to build a model which they would then estimate. They used economic theory to build a little toy model, which they then used to motivate a more careful statistical model, which they then estimated. Actually, the truth of the matter is the statistical model was not much more careful than the toy model, but they didn't estimate the theoretical model. They estimated something else. So you now had a chance to read this quotation from the paper, and basically the puzzle that that criminologists faced in looking at the literature was that if we thought of criminal decision making as being essentially independent across individuals, okay, then if we look at the variation in crime rates across cities, aggregation of individuals, right? That should be determined by the variance in crime rates across cities should be determined by the individual variances in a particular way by aggregation that we all know how to do. Okay, but if you actually look at the real statistics around this, it turns out that the variation in crime rates across cities was actually much larger than that which would be predicted if individuals in cities were making independent decisions. And consequently, how might you, if you want to really study this anomaly in the aggregate data, what might you do? You might look for interesting ways to try and relax the assumption of independence. And this is exactly what social interactions do. Okay, so I'm now going to describe a model that they laid out in the paper. And they actually laid this out. It's the QJE, so you can do little toy models there. They laid this model out and talk about it at length there. And I'm going to talk about it in a slightly different way than they do. But now you can see what I mean by a toy model. They want to imagine that there are an odd number of individuals living on the line, and we're going to label our individuals from -n to n. Okay, so that's our city. Okay, people living on a line. Then it gets worse than that. So hang on. Okay, we have three kinds of individuals. Okay, there are people who are saints, and these are type 0 individuals. They never ever commit crimes. There are people who are confirmed sinners. Okay, these are bad guys. They always commit a crime whenever they have an opportunity. They are what we call career criminals. And then we have people, and these are type 2 people who are people who are, maybe generally nice church-going people, something like that, whatever. But they could be induced in the right environment to commit a crime. When I think about this story, I don't really think about it so much in terms of things like shootings and robberies and what you see on TV, cops and robbers show. I think about this as like tax evasion. Okay, there have been big changes in the United States from basically the 1970s to the 1990s in how people thought about the ethics of tax evasion. And so this is the kind of thing that we're talking about here. So we have these three types of individuals, and type assignments are IID, and that is basically that we have a urn with a certain fraction of saints, a certain number of saint balls, which I'm going to call red balls, certain number, I'm sorry, no, those are blue balls. Our saint balls are blue balls. We have a certain number of sinner balls, which are red. And then we have a certain number of type 2 balls, which are black. And we're going to sample each individual with replacement from the urn. We reach into the urn. I'm going to reach into the urn, take out an individual, okay, look at the color of the ball, and that person is either going to be red, blue, or black. Okay. Once we set this all up, individuals are going to start choosing. Now, how do individuals choose? This is the simplest possible model you can imagine. The saints do what they're going to do. The sinners do what they're going to do. And the type 2 people look to the person to the left of them, to the right of them on the line. Okay. And do what that person does. So they imitate the person, actually, I think the way I've described this in the picture here is that people actually do imitate the person on the left. The arrow points emanating from any individual, the arrow points to the person who influenced them. Okay, that's the convention in the way that we write down social interaction models. So you look to the left and you see what the person to the left of you did. And if they committed a crime, you commit a crime. Okay. This describes a model. This is a model of a very primitive model of criminal decision making. Now, the key thing to understand about this model is how much influence does a given saint or a given sinner have? Right? And that is going to depend upon the fraction of what I will call committed types. The committed types are the saints and the sinners, the type zeros and type ones. The probability of being committed is the sum of the probabilities of being a criminal, being a sinner, and the probability of being a saint. I'm going to call that number pi. Okay. The variance of crime in this population is going to be determined, as we'll see in just a second, by how long are these chains of influence. So if we look at the person on the saint on the left, on the far left here, the blue dot in the picture, okay, that saint induces the person to the right of her to be a saint. So that person is actually going to choose 0. The person to the right of that person is going to choose 0. The next person we come to on the moving to the right is a red dot. That's a sinner. It's not influenced by what anybody does. That person commits a crime. And now we go to the person to the right of the criminal, and what does he do? Well, he's a type 2, and so he chooses to commit a crime. And then whoever's next to him, we look at that type, and if it's an influenceable, if it's not a committed person, then that person will commit a crime. And we keep going through all of the uncommitted people until we reach the next committed person, and then we start again. Okay, does everybody understand? Okay, so that's what's going on. Okay, so let's actually look at the statistics that you get from this. So the first question to ask is, what is the expected length of a chain of influence? And the expected length of a chain of influence is easy to derive. Let's start with, say, our saint on the right on the previous slide. Okay, with probability at 1 minus p2. Okay, in other words, with probability pi, that person to the right of our saint is a sinner. And so therefore that chain has length 0. With probability with probability 1 minus p2, okay. So with what probability 1 minus p2, the chain is of length 0. With probability p2, the person on the right is an uncommitted type. And so the chain is going to be of length 1 plus whatever the expectation of the length of the length of the uncommitted chain going from that person onto the next committed person is. Okay. And these chain lengths, of course, everything in Cite is independent. And so this leads to the recursion relationship that the expected length of a chain is equal to the probability of an uncommitted type times 1 plus the expected length of a chain, plus the probability of reaching a committed type, which is 1 minus p2 times 0. And so this leads to an expected chain length, which is 1 minus pi over pi. Okay. Now we can use this to see how social interactions magnify the effect of fixed agents. Okay, so what is the probability that a given individual is going to commit a crime? Okay, I claim that no matter whether the person is committed or uncommitted, that probability is P1 over P0 plus P1. Why is that true? Well, if the person is committed, conditional on being committed, the probability of being a criminal is a sinner is P1 over P0 plus P1. If that person is uncommitted, you have to look back to the left to see what is the type of the committed person who is influencing him. And the probability that that committed person is a criminal is again P1 over P0 plus P1. And so we see that the expected that the probability of criminality is P1 over P0 plus P1. Okay, now if I label committing a crime as a 1 and not committing a crime as a 0, then this probability P1 over P0 plus P1 is in fact the expected criminality, or the expected number of crimes. You can either commit 0 crimes or 1 crime. So this is the expected number of crimes that a given individual commits. Okay, so now what I want to do is look at the aggregate statistics of this. So in order to, I want to look at the variation around the average criminality of the population. So what am I going to do? I'm going to take each individual's own AI. I'm going to center it around the mean. Okay, then I'm going to sum all of those up and then divide by the number of agents in order to get a population average criminality. Everybody understand? Okay, so we do this all the time, right? This is your first statistics class. You just sum everything. You center your variables around the mean. You sum them up and you divide by the number, and that gives you the population average. So what can we say about the distribution of the population average? There's a computation that you can do. I'm not going to do it here. If we do the usual trick of taking that population average and then scaling it by the square root of the size of the population, we get a limit normal distribution with some which has mean 0 because we've centered everything on the mean, and it's got some variance. And now the question is, what is that variance? Okay, and the answer is that so if these were independent, we know that the variance would be 2 times P times 1 minus P, right? That's the stat1 calculation. But in this model, it turns out, and this is the calculation I'm not going to do that you can check, it is P times 1 minus P times this number 2 times the expected length of the chain plus 1. Okay, so so you can see basically, actually I made a mistake. The variance is not 2P 1 minus P. The variance is P times 1 minus P in the individual case. Okay, and you can see, so if the expected chain length were 0, okay, if everybody were either committed or uncommitted, we get the standard IID result that the variance is P times 1 minus P. But the longer the expected chain length, the greater the variance. And this is the point that Ed Bruce and Jose wanted to make, that the social interaction has this effect of increasing variance within the population. Now, this actually turns out, this is a paper that is now, getting close to 30 years old. But the idea of using variance in order to identify the magnitude of social interaction effects comes from this paper. And there are econometric methods in use today, such as Brian Graham's variance contrast approach to identifying social interactions that essentially stem from this kind of reasoning. I have a paper with Buzz Brock and Stephen Durlop and Rajesh Araman that is in the Journal of Political Economy in 2015 that derives these kinds of variance statistics from a game theoretic model. So this is clearly a doable thing. All right. So now what I would like to do is go on and get a little deeper to talk more about networks. So if we want to talk about social interactions, we have to have a way of talking about social structure. And the representation of social structure that we are going to use is that of a network. We're going to imagine that people are linked by relationships, by various social relationships. And these links are going to determine or in part, they're going to determine how people behave. Okay, so I'm sure that you've seen this kind of thing before. We're going to model social structure by graphs, either directed graphs or undirected graphs. And so before going further, we need to establish some of the terminology of graph theory and social network theory, which the literature uses. And again, just to remind you, there's a rich literature on the study of social networks that is now taking off in economics. I mean, there's now a number of papers that have been written looking at social networks in economics, both from the theoretical and from the empirical point of view. And there's a larger literature in sociology. And in fact, there are entire journals in sociology that are devoted to the study of social networks. And there are many quite good papers there. And sociologists are responsible for many of the fundamental contributions that many fundamental ideas that we're going to be talking about. Oops, I'm sorry, I just did something bad there. Okay. So, let's talk about graphs. So a graph is a collection of objects. It is a set V. It's two sets, V and E. V is a set of vertices. Okay, we can think of, let's just fix this right from the outset in social networks. So we'll have a set V of individuals, and E is a set of edges between individuals. And if you look at the graph down below, you know what I mean by an edge. So I can represent an edge by a pair, the two edges of the that are connected by any of the lines in the graph. Now, these pairs can either be ordered pairs or unordered pairs, depending upon whether the graph that we're looking at is a directed graph or a undirected graph. So a picture of an undirected graph is on the left. You can see that there are no arrows. So AB and BA are the same edge. Okay, and so there is this. If we were to think about this as an influence network, for example, then what we're saying with this kind of structure is that A and B influence each other. And we're also actually saying that they influence each other to different degrees. Okay. I'm sorry, they influence each other to the same degree. Okay. The graph on the right is, in contrast, this is a directed graph. Okay. And so now we have arrows, and there is an arrow from one vertex to another if the second vertex influences the first. So in this picture, B influences A, B and D mutually influence each other, and B influences C. And neither C nor A influence anybody. Okay. All right, so this is the idea. Now, oftentimes we want to have a little more structure than this. Here we just have simple lines, but sometimes we want to talk about the degree of influence. So it might be that B really influences D, but D only influences B a little bit. And so we represent that by putting weights on these edges. And we'll talk about how to represent that momentarily. Okay, so let's move on. The degree of a node in an undirected graph is simply the number of edges that come out of the node. Okay. When we have a directed graph, we talk about 2 degrees. We talk about the out degree, which is the number of edges coming out of a given node or vertex that point to something else. And we also talk about the in degree, the number of edges coming in or pointing to the node. Okay. A path is an ordered list of nodes such that any 2 consecutive, there is an edge connecting any 2 consecutive elements of the list. Okay. If we're talking about an undirected graph, you just have this list of pairs. Okay. But if you have a directed graph, if your chain goes V0, V1, V2, there has to be an edge from V0 to V1, right? The path follows the direction of the arrows. Okay. Some language we'll use later on. A geodesic is the shortest length path connecting any two nodes. Okay. All right. So I should mention, by the way, that there are three good sources for economists for learning about this stuff. And I should have actually said this at the outset. I'm sorry I didn't. There are three books that have been written by economists, and chapter 2 of all three of these books actually has an introduction to graph theory, the things that we're talking about now. One of these books is by Sanjeev Goyal, and it's called Connections. And that's the short title. Then there's a subtitle. I don't remember what it is offhand, but you'll see it in the references. Sanjeev's book was published in 2007. And that was actually the first economics network science book. It was followed a year later by Matt Jackson's book. And, you know, it should be in Cite on my desk, as should Sanjeev's be, but I don't see it. So I don't remember the title of Matt Jackson's book. But it was published in 2008 by Princeton. And again, it too is on the back of the, you'll find the title in the references. And the third book, which is actually the book that I think is the most interesting of the three, is by David Easley and John Kleinberg. John Kleinberg is a computer scientist. David Easley is an economist, and a lot of the good work today in network science is actually being done by computer scientists. And this book has the engaging title, Networks, Crowds, and Markets, and it was published in 2010. Another virtue of this book is that you can get it for free. It's published by Cambridge University Press, but when Easley and Kleinberg contracted with Cambridge to do the book, they stipulated as part of the contract that a PDF of the book be available on their website. So you can go to the website of either of these guys. Well, at least I know you can from Kleinberg, because that's where I got my copy. And you can and you can download it. Which automatically makes it the best book, almost regardless of content, unless you have a favorite Russian website. And your favorite Russian website, at least my favorite Russian website, has all three of these books. Okay. So another good source, by the way, is that there is a survey paper by a physicist who actually writes a lot about social phenomena. His name is Mark Newman, published in 2003 in some SciAm journal. And if you want the short but rather compact introduction to this stuff, you can find it. You can find it there. All right, so let's get back to graphs. A subset of vertices is said to be connected if there is a path between any two of them. Okay, a component of a graph is a collection of vertices which is maximal with respect to the property of being connected. Okay, which is to say it is a set which is itself connected, and there is no other vertex not in the set which is connected to something in the set. Okay, so here is a picture of a graph with 8 vertices, which contains 2 connected components, vertices 1 through 4 and vertices 5 through 8. Okay, in a clique is a particular kind of component. A clique is a component for which is maximally connected, which is to say that all possible edges are in the graph. So the component on the right is on the left is not a clique because there's no edge from 1 to 4 and there's no edge from 2 to 3. But all possible edges in this undirected graph are present in the second component. And so the second component, the component on the right, is a clique. Okay. How do we represent these things in an analytical way that allows us to do things like get them into econometric models? right? We do that by making use of a matrix representation. Okay, there are several different matrix representations. If you get into graphs, if you get into network science at all, you'll discover that there's something called a graph Laplacian, and that is not the matrix that we are talking about, but it's actually useful for studying many properties of graphs. We're going to make use of something which is more primitive. And that is the following. It's called an adjacency matrix, also sometimes called a social matrix. And for an unweighted graph, okay, a graph where we don't have weights, you remember I talked about weights earlier, the ijth element of the graph is either 1 or 0. Okay, it's 0 if there's no edge between I and J, and it is 1 if there is an edge between I and J. Okay, and that's what we. And so I've drawn the I've on the right here. I have put the matrix for this the adjacency matrix for this 8 vertex graph. Now you'll notice that it's pretty clear right away when you look at it that this matrix is a symmetric matrix. And this is because the graph is undirected, right? If there is an edge in an undirected graph between I and J, then there's also an edge between J and I. Okay, and so that's why the matrix is symmetric. If this were a directed graph, then we would put a 1 if and only if there is an edge from I to J. Okay, and we wouldn't put a 1 in the Ji position unless there was an edge going back. Okay, so in directed graphs, these social matrices are not in directed social matrices. These let me start again. Adjacency matrices of directed graphs are not necessarily symmetric. So this is actually too bad, of course, because it turns out that the spectral theory of these matrices is very useful for describing graphs, and the spectral theory of symmetric matrices, as you know, eigenvalues and the like, is all very simple, and it's a bit less simple for asymmetric matrices. If our matrix, if our network is a weighted network, then we replace these 1s with the weights of the edges. And so that's the way that we might say that 1 influences 2 a lot, but 2 influences 1 a lot, very little, by making the 2-1 the 2-1 element of the social matrix large and the 1-2 element of the social matrix small. So then again, if people influence each other to different degrees, even if the fundamental topology is undirected, if they influence each other to different degrees, then we would have a weighted adjacency matrix, and that weighted adjacency matrix will no longer be symmetric. Okay. So different kinds of social matrices describe different kinds of social situations. So one example, here's an extreme example. Let's take a very popular singer, right? I don't know. I actually looked up lists of popular singers last night so that I could think about who would be a good example. And I saw that there is no agreement on who is the most popular singer in the world. I will tell you that I once gave this lecture in China, and I mentioned the name Jay Chou, and everybody in the room went, oh, because everybody knew who Jay Chou was. But if you are from the West, you probably have never heard of Jay Chou. Jay Chou is a Taiwanese singer who is apparently well known, very well known in Asia. So we might think of Taylor Swift, okay, whose music I don't like, just to get that out there. So this is not going to, I'm not going to be an element in this graph. Here is the Taylor Swift social matrix. So Taylor Swift has a bunch of fans. And I've used colors here just because I couldn't make everything fit otherwise. Taylor, of course, is the red dot in the center. Okay, so this is, and then we have all these fans who are on the outside. And so I put them in a little ring around Taylor Swift. And there is a black edge going from Taylor out to each little dot on the edge of this, on the circle, and then there's a red edge coming back in from that person to Taylor. Okay, so why did I draw it this way? So number one, I couldn't put the edges side by side the way you should because there's just not enough room. So I apologize for that. The idea here is that Taylor influences her fans a lot. Okay, so that we're going to think of every red edge going from a black dot to the red dot in the center as having weight 1. Okay, and Taylor, of course, is influenced by the aggregate of her fans, but the influence of any single fan, unless that fan is psycho in some way, so we're going to kind of get rid of them. The influence of any single fan is on her is very small. That's 1 over n, where n is the number of her fans. Okay, so this is an example of a particular set of social relations. Now, we might also imagine that some of the fans are connected to each other. There might be fan clubs, and friends certainly might share an interest in common interests in music, and so we might imagine that there are going to be some interesting edges that along the rim of the circle that I've neglected. But this gives you the idea of how a story about social relations gets mapped into a social network. All right, one more thing. If A is an adjacency matrix, then what is the interpretation of A squared? And by extension, by induction, A to the n for any power of n. Okay, so let's compute A squared of ij, the ijth element of A squared. And the ijth element of A squared is the summation that's on the right of the equality on this slide. Right. So this sum, if we're talking about an unweighted matrix, let's talk for a moment just to nail this down. Let's talk about unweighted matrices. Every term in this sum is either 0 or 1, and it is 1 only if both elements in the product are 1. Okay, so AIK, AKJ is 1 if and only if IK and KJ are both 1. Geometrically, what does that mean? That means that there is a path from I to K, and that goes on from K to J. So there's a path of length 2 through K from I to J. Okay, if we then sum these over all possible intermediaries, we have all possible paths of length 2 connecting I to J. Okay, and so the sum is the number of paths that connect I to J. Okay, and if we add weights, okay, we're just talking about the total weight of all paths of length 2 connecting I to J. Okay, similarly, then if we look at A cubed, it's going to give us for the unweighted matrices, all paths of length 3, A to the power 4 is all paths of length 4, so on and so forth. Okay. Now notice, by the way, that there will be a lot of double counting in drawing these paths. So, for example, if we look at path one path of length 4 from vertex I back to vertex I. Okay, might be going from vertex I to vertex J and then back from J to I. Okay, another path of that's a path of length 2 going from I to J. You go from I to J and then back to I. A path from of length 4 from I back to I is I to J, J to K, K to L, and then L back to I. Okay, so that's a path of length 4, right? But another path of length 4 is I to J, J to I to J, J to I. Okay, so these paths are not simple loops. They might kind of come back and hit different vertices multiple times. Okay, so in any event, we're counting all possible paths, not just all possible loops or circuits or whatever you want to call them. Okay. So here are things that we might want to measure in order to describe a social network. A difficulty, of course, with describing a social network. Suppose you wanted to look at the network of all of all the people living in some village in a third world country, right? There's a data set that's actually collected network data on over 200 some networks in India that was put together by Matt Jackson, Esther Duflo, and Abhijit Banerjee. So these are very complicated objects, right? A graph of size 200. A graph with 200 vertices, could have, many edges, right? It could have 200 times, if it's an undirected graph, it could have 200 times 199 possible edges. What are things so we need some statistics that are going to simplify these things. What are some statistics that are out there? We can talk about graph diameter, which is the maximal length of any geodesic in the graph. We can talk about the average geodesic. One thing that's talked about a lot is the degree distribution of the graph, right? What fraction of nodes have one link? What fraction of nodes have two links? So on and so forth. An important thing that is measured in social networks is the clustering coefficient. So let me explain this. A triad is a path of length 3 with two distinct endpoints. So from person 1 to person 2 to person 3. Okay, that's a triad. We'll say that a triad is closed if there is a third edge going from 3 back to 1, okay, in an undirected graph, okay? So we might think about having two line segments connected to each other. That's a triad. And if it's closed off into a triangle, okay, then we have a story, which is the following story. The friend of my friend is my friend too. Okay, that is that's a saying that you hear a lot in many different languages. The friends of my friends are my friends. Actually, a more common one, say, is the enemy of my enemy is my friend, but we're not going to express that in social networks today. So the friend of my friend is my friend is kind of a fact about a lot of social networks. And what that says is that many triads are in fact closed off. The fraction of triads that are closed off is called the clustering coefficient. Okay, we might, if we were looking at a directed graph, we would be saying that there's a link, an edge from 1 to 2, an edge from 1 to 3, and from 2 to 3, an edge from 1 to 2, an edge from 2 to 3, and then an edge from 1 to 3. Okay, if we think about that as a way of representing a binary relationship of some kind, what it's saying is that the representation is transitive. If the friend of my friend is my friend too, then if that is generically true, then if B is a friend of A and C is a friend of B, then C is a friend of A. Okay, consequently, the friendship relationship is transitive. Now, generally speaking, friendship relationship in social networks is not transitive, but what the clustering coefficient measures is the degree to which it is transitive. How transitive is it? In what fraction of triplets is a potential transitivity actually realized? Another thing that we talk about a lot is something called the component size distribution. How many, what is the sizes of different, well, all right, so we have different components and we can talk about what the distribution of their sizes are. This is kind of an obvious thing, so I will move on. And here is a picture that I'm not going to talk about that you can study on your own to make sure that you can pin these concepts down. What about if we want to do statistics with social networks? So we need a way of statistically describing graphs. So the way that we would do that is just the way we do in describing any thing like height or weight or something like that, we think about the object in question as being a random variable. So just as we can talk about random variables like the height of an individual or something like that, we can talk about random graphs. Okay. And if once we have random graphs, we can ask all of the usual kinds of statistical questions that we do. In particular, we can talk about descriptive statistics of a random graph. We can do inference. If we have a model, a data generating model of random graphs, then we can actually talk about having seen one graph, what another graph drawn from the same data generating process would look like. Or another thing we can do is we can do inference of the following kind. We can say, having seen part of one graph, what can we infer about other parts of the same graph? Okay, these are the kinds of questions that we can answer using the tools of probability and do probabilistic inference once we have data generating processes for graphs. There are two kinds of data generating processes out there in the world for these things. One of them is there's a class of mechanisms that are really purely algorithmic, that just describe how a network is put together. Another kind that ought to be of more appeal to economists, but unfortunately the literature is just not good, is our strategic models of network formation. Now, these things are really important because, you know, if we want to, for example, use social networks and peer effects in studying particular behavior, like, for example, do people smoke? Okay. So if people are smoking cigarettes, why are they smoking cigarettes? So we can look at social situations and we can see maybe that we'll notice a correlation in that the friends of friends are likely. If you are a smoker, your friends are likely to be smoker. So friends smoke together. Okay. That's a positive correlation of smoking with friendship. Okay. Now the question is, why is that true? There's two reasons why that might be true. One is that a peer effect, that your friends smoking influences you to smoke. They're all smoking when you're all hanging out together. Sooner or later, someone hands you a cigarette and you try it and there you are. Okay. So in that case, friendship causes smoking. The other thing that could happen is that basically nobody can stand to be around smokers. Okay. And consequently, the only friends that smokers have are other smokers. Okay. And therefore, we see in that situation, we see that this behavior of smoking causes friendship. Okay. So if we wanted to, so this is a classic inferential problem, right? And in order to talk about that, we need some kind of strategic model of network formation so that we can figure out which way the causal relationship is running. We're not going to have time to talk about them today, but there are a class of models out there. There's something called pairwise Nash stability. There's also something called just simply Nash stability. And there are variations on this. And all of these things are generalizations of something that you probably studied in your first year theory class, which is the Gale-Shapley marriage problem. So if you recall the Gale, this is what's sometimes referred to as non-transferable utility matching. And the canonical story about this that comes from a paper written in the 1960s and therefore justifies the language that I'm going to use is that we have a group of men and a group of women, and we're going to pair them off into relationships. Okay, and a pairing of individuals is said to be stable if there are no two individuals matched to other people who want to break off their relationship so that they can match together. Okay, so there is a relationship is a pairing of individuals or a pairing of the whole population of men to women, women to men is said to be stable if nobody wants to divorce, so that if there's no couple that wants to divorce their partners so that they can remarry. All right, so that is, you've learned about that in your first year theory class, at least if you had a good first year theory class, you did. If you had my first year theory class, you did. And that idea has been taken to general social networks by Matt Jackson and Asher Walensky in a paper published in JET. And what do? They say, let's imagine that individuals have utility functions for networks, okay? And we will say that a network is stable, is pairwise stable, pairwise Nash stable, if number one, nobody wants to drop a link that they have, okay? They won't, if we drop a link, we move to a new network, because that new network can't be better. And then another way of moving to a new network is to take two people who are not linked and link them together, okay? And that cannot improve the utility of these two unmatched people, okay? So that's the idea of pairwise Nash stability. And it is an obvious and straightforward generalization of Gail Shapley's idea of stable matches. And by the way, that's an example of something called the bipartite graph, because we have two kinds of vertices. And every vertex of one kind has to be linked only to vertices of the other kind. So that's the idea of pairwise Nash stability, and all the other stabilities are basically variations on that. And the problem with this is that they don't always exist. And if they don't always exist, then, and also we don't have, outside of some special cases, we don't have general theorems about their existence. So it makes it a little hard to do research with them at the moment. So this is maybe not exactly yet the right concept, although it's clearly on the path. I noticed that there are a number of comments in the chat, and I find it really hard to monitor the chat and talk at the same time. So what I'm going to do is, when we stop for a break, I'm going to read the chat, and then I will make comments on that. And I want to get a little bit farther before we take a break. But we're almost there. I want to talk briefly about two more ideas. I want to talk about how this notion of random graphs works. So here's one example of a mechanism for constructing. Here's a random graph generating process, a data generating process for a graph. We take a set of vertices, and we pick up two vertices, and then we flip a coin, and if the coin comes up heads, we draw an edge between them, and if the coin comes up tails, we don't. Okay, so if we flip all the coins for every possible edge, then we end up with a graph. Okay, and there are a number of questions that we can ask about that graph. How many components does it have? What do the component size distribution look like? So on and so forth. And we can ask that in a probabilistic way as well. We can say, what is the probability, for example, that the graph will be connected? Or what is the probability that the mean degree will be greater than or equal to 4? Things like that, right? So these are the kinds of questions that we can ask with a data generating process for our random graph. So this random graph that I've described is called the Erdős-Renyi random graph. Naturally, it's named after two Hungarians. And it is also sometimes called the Bernoulli random graph because of its obvious connection with Bernoulli distributions. Now, the fun thing to do with this is not to kind of look at the Bernoulli random graph per se, but to take interesting limits and look at large networks that are constructed this way. If you fix the probability of drawing an edge between any two people and then let the number of vertices grow, what happens is that the degree of every individual grows, and it grows at the mean degree grows at a rate equal to basically it grows at the order of the size of the graph, okay? That's not a very interesting graph because most of us, for example, are not connected to a large fraction P of people in the world, right? Another way of another kind of limit thing that we do with Bernoulli random variables, right, with, is the following. We let we let n get very large, and we shrink p so that the mean number of occurrences. So imagine that we're going to flip coins, and and the probability of getting ahead is P. And we're going to flip the coin n times. So now what we're going to do is we're going to let n get very large, but we're going to shrink P so that the mean number of flips remains constant. Right? Now, you might remember this. All of you have seen this in a statistics class because the limit distribution that we get from this is the Poisson distribution. So we can do the same thing in a graph. We can let P get small as n gets large in this graph construction model, such that the mean degree converges to a constant, which I've called on this slide Z, and that gives us something that we might call a Poisson random graph. And the reason for bringing this up is that it's the first example of a very general property of random graphs, and it also shows some of the cool things and surprising things that we can learn by looking at random graphs. So there's a lot of cool properties about these graphs, but one is a phase transition of a particular kind in the graph. And you probably read the slide by now so that you can see it. The key idea is the following. We can look at the size of the largest component of the graph. Okay, when P is very small, this is obviously going to be a disconnected graph, and it's really only going to be connected for sure when P is equal to 1. Okay, so typically there will be many components. And what does the size of the largest component look like? All right, well, when Z is a number less than 1, Z, remember, being the mean degree, when Z is less than 1, the size of the largest component grows like log n. All right. So, and log n over n is a number that converges to 0 as n gets large. So it means that even the largest component essentially contains a negligible fraction of the population as n gets large. When the mean degree is greater than 1, a different phenomenon happens. The largest component grows with n at a rate equal to, it grows at order n. Okay, so that as n gets large, a positive fraction of the population will be present in the largest connected component, which is referred to in the literature as the giant connected component. And it's called the giant connected component is because it's called that because another general fact about random graphs is that the largest connected component, when we're in this supercritical regime where we have connected component growing at order n, the largest connected component is in fact unique. There won't be 2 distinct connected components growing at rate n, there'll only be 1. And that's actually a probability 1 statement. So I've drawn, there's a picture here that I stole from somewhere on the internet. I don't remember where somebody, drew 300 random graphs for different values, for many different values of Z. And you can see what how the size of the largest component grows very, very slowly with as Z changes, the fraction of elements in the largest connected component grows very slowly with Z until Z crosses 1, and then wow, it really takes off. Okay, so this kind of phenomena where it takes off is called a phase transition, and there are lots of phase transitions in the behavior of random graphs. Okay, so that's what I wanted to say about the Bernoulli distribution. Another important class of random graphs are what are called scale-free networks. Scale-free networks are networks that have power law distributions. I put a couple of facts about power law distributions on this slide if you don't know what they are, but basically these are distributions that have thick tails. All right, so they're distributions that have tail behavior that looks like alpha x, tail behavior described by a density, which is alpha x to the minus gamma. That's upper tail behavior, alpha x to the minus gamma. And if gamma is greater than 1, variances and kurtosis and things like this won't exist. If gamma is greater than 2, even variance won't exist. So these are graphs that have interesting property. Actually, it's the other way around. If gamma is less than 2, then the variance won't exist. If gamma is less than 3, then kurtosis won't exist, so on and so forth. And this is because the tails are thick, so that when you compute these integrals, the integrals don't converge. Okay, here's a mechanism for growing power law distribution graphs that has been used to model things like citation networks. There'll be a link between paper A and paper B if paper A cites paper B, okay, from A to B if paper A cites paper B. So we'll have a vertex set of size n. Okay, and I've described here, you can read this, what this mechanism is with probability 1 minus p. A vertex I links to its immediate predecessor, and with probability p, it links to a randomly chosen node going that we already, from with labels from 1 up to I minus 1. Okay, so this is always going to give us a connected graph. Because you are making a connection. It's either going to be to your immediate ancestor, I to I minus 1, or it's going to be to something randomly chosen, okay, earlier on. And what this process does, is give us a degree distribution, which is a power law distribution. And I've given you a citation to a paper that actually describes does a probabilistic analysis of this process in some detail. And this preferential attachment story kind of makes sense. If you think about what you do, you all have written papers, and you are busy thinking strategically about who you have to cite in order to get your paper published, right? And the object of citations is not to make angry some potential referee, okay? Or the referee will say, you can't publish the paper because this person didn't quote me enough, okay, cite me enough. So how do you do that? Well, the first thing you do is you cite recent papers, okay, because those are the papers, authors of whom editors are going to select for referees. And then the other thing is you have to make sure that you cite the famous papers, namely papers that are farther back in the chain of your literature. And that's exactly this process. And it turns out that preferential attachment model is a good model when it's been taken to citation data in physics and in the sciences and in other literatures. Okay. Here are some pictures of what preferential attachment graphs tend to look like. We will skip that. Here is a picture of a social network where where the researchers went into an American school, okay, and they asked they asked after social relationships, who's your boyfriend, who's your girlfriend, right? This was done, I think, in the 1970s, or 1980s, I don't remember which. It was done by a sociologist named Peter Baer, who is at Columbia University. Blues are red, pinks are that's crazy. Blues are boys, pinks are girls, okay? Most of these, this is not entirely, but it is largely a bipartite network, which is to say that it is mostly boys linked to boys and girls linked to girls. I'm sorry, that is exactly the wrong thing to say. It is mostly boys linked to girls and girls linked to boys. There are a few exceptions. You can amuse yourself trying to find them. Okay. You can also see what we mean by the giant connected component here, because here we have in the upper right, we have a very large connected component of people who have been involved in relationships with lots of others. And we can see that there, by the way, are relatively few people who have been exceedingly promiscuous. Okay, but there are just a few people who are, but nonetheless, we have this long chain, okay, or this long connection of people. So this is a typical social network. Here's another one that comes from another American high school. This paper was written by James Moody and co-authors, and this is a friendship graph. And this is a lower SES high school somewhere in the United States, in the Rust Belt. I don't remember exactly where. And in how do we interpret? You'll notice that one of the things that we try and do in drawing pictures is to label the nodes, to have, it's not just the edges that we care about, it's also the node information. In this case, we care about the ethnicity of the students. And so green nodes are Black students. Yellow nodes are Hispanic students, and the pink nodes are all others. And what we notice in this friendship graph, the other thing to notice about this graph, or that's true about this graph, it's drawn in such a way that the age of students is increasing more or less as you move upwards in this picture, as you move from bottom to top of the picture. So what do we learn from this? We learn that friendships cluster by age, and they also cluster by race, okay? And we get a sense of the relative strengths of these things by looking at this picture. But of course, you can't actually do statistics with pictures very easily. And so fortunately, and thus all of our emphasis on graph statistics. And I think I'm going to not talk about this. This is a good moment at which to take our break, I think. Is that right? Is anybody here?
Yes.
Yes.
Okay.
Yep.
I can see, I think there is just one question in the chat from Annie Tubaji.
Right.
Please let me know if you want me to read it.
Yes, I'm reading it right now.
Okay,
And if
that's
Annie
good.
is here, I will
Thank
give
you.
her actually an oral answer right at this moment. And my answer is that I don't find it useful to think about what kinds of claims are economic and what kinds of claims are sociological. Those are just labels that we stick on people, but we're all studying the same stuff. And in fact, our disciplines are really quite merged, right? I mean, rational choice. So I sit in a university that has a sociology department that's known for being a center of rational choice sociology. And the statistics that the sociologists downstairs were also a place that spends a lot of effort studying income and wealth distribution. And the work that comes out of the people downstairs, they're on the floor below where I'm sitting right now, is actually, would meet the standards of any econometricians. So I'm not sure that, at least as well as any randomly chosen economics paper would. So I'm not sure what's sociological and what's not. I think that the way to think about this is, in doing your research, is what you care about the individual or the system. All right. And so when I read a paper and that paper says that if I do treatment X, individuals are going to do this. Okay. That's a paper about individuals. Okay. If I look at a paper that says if treatment X is applied, the social system changes the following way. Okay. That is a statement about social systems. Okay. I agree with your point that there's actually, there actually is, there is a lot of there is something called behavioral game theory. And there are no, it's a vibrant area of game theory, but it's really studying small stuff. What we're really missing are large empirical studies. So let me give you an example of the kind of thing that I think we're missing. There's a lot of work on how we can use nudges to help people improve their labor market situations. Okay, so how can we nudge people to be more active in searching for jobs? Okay, that is, there are papers that are written on this. Okay, but what I cannot find papers on is, and the way that these are typically done, by the way, are doing field experiments. All right. So where we'll take some group of people and we'll give them some treatment in some community in some town or something like that, and then we'll see what happens. And then we'll find that maybe because of our treatment, because of our nudge or whatever it is, people search more aggressively for jobs. Okay. Now, the question that I have is, suppose that we were to actually do this at scale, okay? So that everybody starts searching more aggressively for jobs, right? You know, the rate of job closure that you're going to see, the rate at which people find jobs, when you do it in a little field experiment, is going to be different than the rate that you're going to see when everybody, you know, who's unemployed is essentially being nudged the same way. Because if the search intensity of a few individuals increases, they're going to have more success. But if the search intensity of this entire population increases, it just means that everybody's all searching harder, right? But the number of jobs remains the same, okay? And so, you know, it's not going to have a bigger, it's not going to have any effect on unemployment. All right. So you will have an, you know, and furthermore, not just will it have any effect on unemployment, but the probability that you being nudged is going to, I want to say this the right way. If we did this to everybody, and you know, if we treated everybody in the population this way, the probability that any individual lands a job will not change, because everybody's search intensity has gone up, but the number of jobs has remained the same. Okay, so when everybody is searching at a low intensity rate, the jobs are getting filled. Okay, to, you know, some jobs are getting filled, you know, and some people are finding jobs. But if the number of jobs is remaining constant, okay, then we can't create. We don't have more jobs for everybody to get into. So the chances of finding a job over a long enough, you know, over a long period of time are going to remain the same. Now, there'll be a short run impact because maybe jobs will fill quicker, okay, but there'll be no aggregate impact. So the aggregate impact of the field, you know, you can't infer anything about the aggregate impact from the field study. That's my point. That's really what I think game theory is about. I've been reading lately several histories of the Cold War. Now, the Cold War to you is like the Peloponnesian Wars, you know, that happened. Peloponnesian Wars were in ancient Greece, right? It was Athens versus Sparta. The Cold War was, you know, the East versus the West, the Russia versus the United States, pardon me, the Soviet Union versus the United States. This also happened in the ancient past, okay? And people, you know, when game theory was essentially founded, or early research in game theory was essentially funded by people who were trying to study the Cold War and study these, you know, personal interactions. So we had these two countries, you know, playing a game that, you know, that might be a zero-sum game. What should they do? Okay. Game theory, I think, is remarkably unsuccessful in studying two-person or two-player interactions, in the sense that we have very, very nice theorems, but it turns out that empirically, they're really pretty useless. And if you read histories of the Cold War, what's really striking is how bad game theory is. Because, you know, the idea of Nash equilibrium, right, is that everybody has correct expectations. And you listen, for example, you read what was going on in the minds of the Soviet controllers during the Cuban Missile Crisis. And you read what was going on in the minds of the American controllers during the Cuban Missile Crisis. And documents are now available so that you can actually see what, you know, minutes of meetings where these two sides, and you realize that they have completely different beliefs about what, you know, the others, from what, you know, each side completely misunderstood the other side. And it's just remarkable that we didn't blow the world up. Right. So two-person game theory, small group game theory, I think is kind of a waste. I think that game theory is most effective when we study large groups, when we actually study social interactions. And what behavioral game theory has not done is to move from small groups to large groups. And what most behavioral economics has not even gotten to game theory yet. Right. So that's the path. If you're a behavioral economist sitting there, there is low-hanging fruit. You can write really foundational papers, get your Nobel Prize, right? I can think of one economist, by the way. I already know one economist who won a Nobel Prize for his thesis research. Okay. So that could be, the next one could be you. Okay. I can only name one, but you can't count the very early prizes, because who knows what those prizes were actually for. They were for famous guys, and they were all guys, right? But if you start looking at the Nobel Prizes of the last 20 years, they're all for particular papers, particular pieces of research. One of them was actually for a thesis, okay? The next Nobel Prize winning thesis could be yours if you start thinking about how to do behavioral game theory at scale, okay? If you were actually in a class of mine, I would demand that you were, I mean, if you were my students, I would demand, by the way, that you turn on your cameras, because it is bad to see a list of names rather than just people. And Olga Novakova, how are you?
Thank you very much. Yeah, thank you very much.
Are you still skating?
No, actually, I didn't do it for a long time.
I'm sorry to hear that, because I really liked those videos. I thought they were, I was very.
Thank you very much.
Did you ever write that paper on wine?
No, actually, now I'm more on social inequality. So I changed my interests, and now I'm more interested in gender.
Okay, well, I actually was talking to Jean-Philippe not long ago, and we were wondering about that, because he and I still think that paper is a surefire paper at the QJE, if you were ever to write it up. Okay, and it's very nice to have a top 5 paper when you're looking for a job. So, you know, take a break from what you're doing sometime and just write that paper. That was so cool. Okay.
Oh, thank you very much. I had some problems with data, but yeah, because
if someone that says that I didn't have any problems with my data, then I don't really believe they did. So they made up their data set. So anyway, I'm glad that you're here.
Thank you very much.
So you hang around, those of you who are listening, you hang around NES long enough, you know, there is a pool of people you'll get to meet again and again and again. So, by the way, you've heard this lecture before, Olga. So you can send me a comment privately, I hope, afterwards, and tell me which version was best.
But I changed dramatically after this time, so.
Okay, right.
I had graduate studies in economics, so that's why now I'm more ready to implement what you said. I will try to implement it in my research.
There is a literature on does studying economics change you as a person? Okay, there is a paper by Bob Frank on this topic, and an experiment that was done was the following: seats in a classroom were filled randomly with unsealed envelopes containing a $1 bill, okay? And the envelopes were stamped and addressed, okay? And so that's the setting, and the outcome variable is whether or not the envelope is mailed, okay? And the treatment is whether you are in an economics class or whether you're in an English class, okay? And the person who did this hoped to find that economists were less likely to return, to drop the envelope into the mail. And the inference being that they were keeping the $1. Okay. Now, I'm very glad to report that actually what happened, that it was the English students who were less likely to put the envelope into the mail. Okay. But what we don't know, right, was whether they kept the $1 or they were just, you know, kind of too slow. They didn't even open the envelope. They just left it there. So we don't know. But I have to say, I'm very glad that experiment came out as it did. All right, so we should get going again, and I'm going to shrink this down to a useful size. Okay. And let's talk about centrality. Does everybody see a slide that says centrality? Give me,
We do.
Yes.
You do. Okay, good. All right. So here's an important question. Oops, that's not where I want to be. Okay. Maybe it's no. I keep forgetting. I have a new computer, and I don't know whether it's 2 fingers or 3 fingers that get me to where I want to go. Let's see. Blah 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 blah. Hang on. Okay. So, natural question to ask about a network is, who are the central people in a network? And the answer to that question is going to be, well, what do you mean by central? So let me give you 2 examples. One example is we want to know who has the most influence, whose behavior has the biggest effect on everybody else. Okay. Another one is if we think about celebrity networks, that might be the question that we would ask. Another question to ask is, who is the person who knows the most? Okay, who knows the most about what's going on in the network? If we're studying information diffusion, information transmission in a network, that's the relevant question to ask. Yet another question to ask is, and this is a question that is studied in marketing departments, how many of you have heard of something called viral marketing? So the idea of viral marketing is that you hire people called influencers, right? So this actually gets back to the first thing, who's the most influential thing? From whom is stuff going to diffuse? Okay, so it's really only 2 things there. How do we measure? So we have these 2 different ideas about, who is most in the flow of things and who is the most influential. These are kind of different ideas. How do we measure these things in a graph? What properties of the topology of a graph are going to determine, or at least help determine, the answer to that question? So there are many types of centrality notions developed in the literature. There's degree centrality, which measures how many vertices can a vertex reach directly. So if you're interested in direct influence, that's what you want to know. Betweenness centrality, how likely is it that a vertex is on a geodesic that connects 2 randomly chosen other vertices? If you're thinking about information flows, right? Who is going to be the most likely to know something? They're going to be the person who is most likely to know something is the person who is most likely to be on a geodesic, because information transmission is clearer the shorter the path, right? So if you're on a lot of geodesics, you're going to hear a lot of stuff clearly. Closeness centrality. Who is, for every individual, we can say, how far are you from the edge of the graph? We can formulate that question by saying, what is the maximal distance between you and anybody else? All right, so remember, how do we measure distance? We measure distance between any 2 people by the length of the number of edges in the geodesic, the number of edges in the shortest path connecting them, okay? The maximal distance between you and anyone in the graph, what's the longest geodesic from you going out to anybody, okay? And then we'll say that you're central in terms of closeness if the length of that geodesic is relatively small compared to other people in the graph. If your geodesic is smaller than everybody else's, then in terms of closeness centrality, you're the most central. And again, if we think about if I want to start a rumor, who do I want to talk to? I want to talk to someone whose closeness centrality who's very central in terms of closeness. The most subtle kind of centrality is something called eigenvector centrality. And it goes like this. Someone is said to be central, or someone is said to be important, I guess, if they influence other important people, okay? Now, the difficulty with that sentence is that it seems self-referential, okay? Because in order to figure out who's important, I have to know what important is. And that suggests that there's going to be an equation to solve that will give us an answer to this. It's going to be some kind of, equilibrium condition of some kind. So let's actually see how we can use the adjacency matrix to compute these things. First, which nodes are important? Degree centrality is simply the column sums of the adjacency matrix, okay? And I put the formulas on this slide so you can see them. And we're talking, by the way, typically we're usually interested in influence, so that we would be talking about in degree. Okay, let's talk about eigenvector centrality. The way that that we'll express this is by saying the centrality of J is proportional to the sum of the centralities of the nodes that J influences. All right. So if I take that idea, I can write that down in an equation form by the equation on the left that says that the eigenvector centrality of node J is equal to mu. Mu is going to be our constant of proportionality. And what is the sum? It is the sum of the vertices that I am connected, that J is connected, that J influences. It's the sum of the i's that J influences, each weighted by its centrality. And there should be a superscript E on that C. I'm sorry, I didn't put it there. And so that gives us the matrix equation. CE is equal to mu times CE times A, okay? What does that tell us? That tells us that eigenvector centrality is going to be a left eigenvector of the matrix A, the adjacency matrix. And by the way, this works as well for weighted adjacency matrices as it does for unweighted matrices. And furthermore, that the eigenvector of A is equal to 1 over mu. Okay, that won't interest us so much, but the fact is that C is a left eigenvector. Now, if the eigenvalue mu were a complex number, this wouldn't really make a lot of sense, right? And for that matter, if the only solutions to this kind of equation were complex numbers, in other words, if all of the eigenvalues of the matrix A were complex, this would be a useless idea. Fortunately, that's not the case. There's something called the Peron-Frobinius Theorem, which has to do with irreducible, non-negative and irreducible matrices. And in our framework, this corresponds to networks, directed networks or undirected networks, but directed networks that are totally connected in the sense that there is a path between any two vertices in the network. Okay, so that if everything can be reached from everything else, the adjacency matrix, whether it's weighted or unweighted, will be irreducible. There's a linear algebra definition that is not related to networks that you can look up if you go to a linear algebra book. And the Peron-Frobinius theorem says that if we have a non-negative irreducible matrix, there is a unique scalar mu, which it has the maximum absolute value of all of the eigenvalues of the all the absolute values of the eigenvalues of the matrix. Furthermore, that eigenvalue is a real number. It's not a complex number, and it's also positive. Okay, so mu will be greater than 0. And furthermore, we can also show that the any left eigenvector corresponding to this eigenvalue will be strictly positive. And what we will do typically is normalize, there's a whole array. Another thing I should say is that the eigenspace corresponding to this eigenvector has dimension 1. In other words, that there is the eigenspace corresponds to a particular left eigenvector and all scalar multiples of it. There's basically, if we normalize by taking the sums of the coefficients to be 1, then there's only one such eigenvector, and that will be our centrality vector. This idea is due to a sociologist whose name is Phil Bonasich, who teaches at UCLA, still teaching, I believe. And he wrote this paper back in 1987. This idea has a lot of lift, and we'll see some of that shortly. Here's another notion of centrality. This is due to a guy, Leo Katz. Leo Katz is, I'm sure, not teaching now since he wrote this paper back in 1953, when at most one of us on this Zoom call was alive. It's a measure of closeness centrality. So we'll assume that our matrix is we have an adjacency matrix, weighted or not. It's irreducible. And what I'm going to do is, because it doesn't matter for this stuff, I'm going to normalize the matrix by multiplying it by a scalar, so that the maximal eigenvalue, the Peronfrombinus eigenvalue, is 1. By the way, I should be a little bit more precise. So there will be one. There will be a positive real eigenvalue that takes on the maximum absolute value, or the maximum modulus among all of the possible eigenvalues of the matrix. But there could be others as well that are also complex. There's another property called primitivity, which basically means that you can't break these paths, that there's not a kind of a cyclic thing going on, okay? And if the matrix is primitive as well as irreducible, then there will be a unique eigenvalue of maximum modulus. And so we're going to divide our matrix by, multiply it by the scalar 1 over that unique eigenvalue of maximal modulus, so that we can assume without loss of generality that that the matrix A has eigenvalue 1. And then you can transfer these ideas back to other sizes if you want. Now, when will a matrix have an adjacency matrix also have the property that it's primitive? It will have that property if there are 2 paths in the matrix. If there are two cycles. If we think about paths that start at individual I and then come back to individual I, if anywhere in the graph there are 2 cycles that are relatively prime with respect to each other, in other words, that their lowest common denominator is 1, if that's the case, then a matrix will be primitive. By the way, the Peron-Frobinius theorem, I should have said this, actually comes up all the time in talking about Markov chains. And I suspect that many of you have studied Markov chains. And a lot of the things that you know about Markov chains can be transferred over into the study of any other kinds of non-negative square matrices that you come across. So for example, input-output matrices in growth theory, Markov chains, social matrices. So there's kind of, linear algebra isn't that big. And so there's a small set of theorems that cover a lot of ground. All right, so let's look at Katz centrality. I define it. Here's what I do to define Katz centrality. Let's look at the ijth. Let's look at this sum. So let's go to the interior sum, and let's look at the matrix A to K, a to the power K. All right. We know that this matrix, okay, tells us the number of paths of, or the weighted number of paths of length K. From, if we look at the ijth element of A to the K, it's the weighted number of paths of length K connecting I to J. Okay, so when we look at the for a particular K at alpha to the K times the ijth element of A to the K, right? What is that? That is the maximum number of weighted paths from I to J, but we've now discounted that path by a discount factor corresponding to its length, namely alpha to the K. So what we're doing is we're looking at the number of paths. Basically, what Katz centrality does is it looks at the number of paths connecting I to J, but discounts longer paths at rate alpha. Okay, is that clear? Let me say that one more time. What Katz centrality does is it looks at the number of paths coming in to the Katz centrality for individual J is the number of paths coming in to J, okay, but paths are discounted by their length. So longer paths get less weight than shorter paths, okay? Graphically, we can, I've given the matrix expression for this on the right. E is the matrix, E is the row vector of containing only ones, of all ones. And so when I pre-multiply a matrix by that row vector, what I'm doing is taking column sums, okay? Finally, I've given you a more convenient expression for this than having this infinite sums at the bottom on the right. The row vector of Katz centralities is alpha times the scalar E times I minus alpha A inverse times A. Why I minus alpha A inverse? Well, I minus alpha A inverse is the has the power series expansion I plus alpha squared A squared plus alpha cubed A cubed, so on and so forth. Okay, and then in order to get Katz centrality, we don't want to start with I, we want to start with A, so we just multiply everything by A. So
is there an upper bound on what A can, or on what alpha can be?
Well, actually, yes, because so alpha needs to be, this doesn't make sense. So actually, it turns out that I minus alpha A inverse can exist, you know, will typically exist, right? But the power series expansion only works for an alpha which is positive and less than the inverse maximal eigenvalue. All right, so for our matrices, I've assumed these eigenvalues are 1, so alpha needs to be less than 1. Okay, good question. All right. Yeah, because the bottom equation always works, but it doesn't express what's in the top equation on the right unless alpha is less than the inverse maximal eigenvalue. All right. Now, this is really good, I suspect, for comparing two individuals in the same network. But there's actually a way of manipulating Katz centrality so you can get it to say a lot more. So alpha, you know, as alpha converges up to 1, the centrality vector is going to become unbounded. Okay, and when alpha is equal to 0, it doesn't say anything. You know, it's just 0. So I want to just modify this a little bit, and I'm going to define C prime alpha to be 1 over alpha times the C prime of alpha to be 1 over alpha times CK of alpha. Okay, and what this does is actually get rid of 1 power of A. And now if we do that, we have the expression that's in the center of the inequality. And now you can see that if we take Katz centrality divided by alpha and then take the limit as alpha goes to 0, what do? We get the degree centrality. Okay. All right. And that's just an algebraic calculation, and that's a useful fact. Let's do one more transformation. So when we look at Katz centrality, we're looking at you can think of it as looking at present discounted values. Now, whenever I see a present discounted value, I want to turn it into an average discounted value because that allows me to compare many, many, many more things. What is where have you seen average discounted values before? If you remember from first year theory, if you ever in a game theory class looked at the Folk theorem in game theory, and there's this idea, right, that that many outcomes can be Nash equilibria in repeated games when people's discount factors are very near to 1. Okay, the way that one looks at that is by actually looking at average discounted values rather than present discounted values of utility streams. How do you get an average discounted value? You take the present discounted value and you multiply it by 1 minus alpha. Okay, and so if we do that and we apply that to Katz centrality, so that we define a new eigenvector centrality, or a new vector centrality vector which I call C tilde K of alpha. And we just say that that's 1 minus alpha times alpha divided by 1 minus alpha over alpha times the Katz centrality vector. that has the following properties. As alpha goes to 0, it gives us degree centrality. As alpha converges to 1, it gives us n times eigenvector centrality, and you can prove all of this for yourself. So this gives us a way of using the centrality vector, the Katz centrality vector, for comparing not just two guys in the same social network, but it allows us to compare two people, or to compare different social networks. And I can ask, in different social networks, where is centrality more evenly distributed, right? So you might imagine in the network where everybody is influenced by the person on their left, and furthermore, they're all connected in a circle, okay? Everybody's going to have equal centrality. On the other hand, it's not hard. This is a homework exercise. Compute Katz centrality for the celebrity network that we talked about earlier, the Taylor Swift network, right? And so now we can actually make meaningful comparisons about in which network is centrality more evenly distributed and in which is it less. And it's rather obvious in this comparison, okay? Another thing we can do when we have networks that have some, we can, and we vary alpha within the network, we can see that as alpha grows to 1, what we're doing is we're putting more and more emphasis on longer paths. And when paths are very short, right, some people might be very central. When paths are very long, different people might be very central. And we can construct graphs where you can see that kind of transition going on. Now, I spent a lot of time talking about Katz centrality because it's going to come up right now in a game theoretic model that I want to describe very briefly. Homework problem. Everybody has to do homework. Okay. Send the answers to Alyona, who will then do I don't know what with them. Okay, but don't send them, Alyona, to me to grade. So I'm done with grading until the fall. Here's another notion of centrality that's actually due to Phil Bonasich and a co-author of his. It says that centrality is about who you are connected to and also what you bring to the table. Okay. So we have an expression that's going to give us something that looks like eigenvector centrality. This is his fundamental equation, their fundamental equation. C alpha of D, D is what you bring to the table, is defined to be alpha times essentially what's going to be, this is going to turn out to be something like your eigenvector centrality, the first term. And then the second component is something that you might bring from the outside, like just, some outside social status that you have, or you're doing something so visible and so extreme that even a little exposure to it influences people a lot. It can be a lot of different things. If we go down and take the present discounted value version of this, we see that this is actually closely related to Katz centrality. If you want to know more about this, you can read this paper by Bonasich and Lloyd. And I am now going to show you how we can use these centrality ideas. So here's a game. So this is the first game. We're going to conclude this talk by looking at games on a lot of different social networks. Okay, so here is a canonical story. Now I've been a very bad guy here because whenever I see a game, and if you ever write a paper that has a game in it, this is what you should do. You need to be very clear about saying, what is the player set? What are the actions available to the players? Okay. What are the payoff functions available to the players? Okay. And I actually haven't really done this here with any care, but so I'm going to now say this is an n player game, and these players live on a social network. Okay. And if there is a link from I to J, then J influences I, and the weight of that weight is equal to J. Is equal to AIJ. Now I'm going to think about this as a pure effect model of where every individual is interested, or every individual responds to the average play of others in the network. Different people, though, are going to have different social groups within the network. So different people are going to average in different ways. Okay. So what's going to be true is, since everybody is averaging, that the sum of the aij's over j, the row sums are going to all be 1. Okay, and so the sum over j of aij xj, which I call x bar I, is just the average behavior of the people that I responds to. Okay, and for different people, different i's, that's going to be different averages. Now, how does that influence payoffs? If we look at our payoffs, we see that there's 2 parts. So strategies, actions are going to be numbers on the real line. Okay, there are 2 components to payoffs. First, let's look at hi xi minus xi squared over 2. That is the private component of utility. Okay, and if you are maximizing, if person I is maximizing by herself, and there's no social component involved, payoff, if beta in this expression is equal to 0, okay, then she's just going to maximize hi xi minus xi squared over 2, and xi is going to equal hi. So hi is what she likes best. Okay, but on the other hand, she is also influenced by the behavior of others. Right. And the farther away she is from the average of her peers, the more disutility she experiences. So the second term is minus beta over 2 times xi minus x bar I squared. We're measuring distance from others by square distance. Okay. And beta essentially gives us the marginal rate of substitution between private utility and this public component. The larger is beta, the more important is the public component of disutility, of being different from the average, right, relative to the private component. All right, and I'm going to assume for much of what we do here that the betas are all the same because it makes everything a little bit simpler to describe. So you can write down, so what do you want to do to solve this thing? Your natural instincts, all of you, I'm sure, is to write down the first order condition and pray that they have something to say. And of course they do, because for 2 reasons. Number one, this is a concave problem. So the first order conditions actually are going to describe optima. And second of all, because everything here is quadratic, the first order conditions are linear in xi, which means you can actually solve them. Okay, both of those things are important. Okay, and when you solve out the first order conditions, you get an equilibrium, and it's a unique equilibrium. And the important parameter is this number beta divided by 1 plus beta. So this number phi gets very large, converges to 1 as beta gets very large, and converges to 0 as beta converges to 0. Now, so what do we have here? We have 1 minus phi times I minus phi A inverse times H. So this, 1 minus phi times I minus phi A inverse seems like it's related to the centrality stuff that we were talking about earlier. A natural question to ask if you are a social scientist studying the social network is to say, what is the average play in the population? Okay. So it's like the sample average, right? What is the average in the population? Well, so what do I want to do? I want to sum up all of the xi's, right? All of the terms of the x vector, which is and divide by n. Okay, so remember that x is a column vector here because h is a column vector. You can tell it's a column vector because it's appearing on the right of the first order condition, or the right of the solution equation. It's the only way it would make sense. So we're taking the column vector x, we're pre-multiplying it by the row vector e, and that gives us the sum of all of the components of the vector h, and then we divide by n. And now if you do a little bit of linear algebra here, you see that the average play of the population is equal to 1 over n times the Katz centrality vector phi times the vector h. So if we were to ask, one question to ask is, well, who is the person who has the biggest influence on average play, on the average play of the population? And the answer is that it is the person with the largest Katz centrality, okay, measured at parameter phi, where phi is given to us by the strength of the public versus private trade-off. I think that that's really remarkable, that this immediately translates right into this, this economic question has an immediate answer in terms of Katz centrality. Furthermore, that this utility parameter beta, which measures the public-private trade-off in each individual's utility, is directly represented in terms of the Katz centrality. It tells us which Katz centrality we want to look at. Now, the bigger is beta, the nearer phi is to the critical value of 1, and the nearer C tilde K of phi is to eigenvector centrality. Okay, so what's happening is that longer and longer paths become more important as beta grows. All right, which I think is not surprising. So this is a very nice this is the kind of thing that this is an interesting way in which centrality emerges. Okay, so now let me go on to a different topic. Okay, we're going to come back and talk about well, we're not going to have time. If we had more time, we would come back and talk about more games. Okay, and we'll see if we want to do that. So let's talk a little bit about labor markets, and let me skip this and move right on to talking about job search. So I want to talk about a different feature of social networks. So obviously, when we're studying behavior on social networks, you know, we're going to run some regression, and that regression is going to, you know, have a lot of information about individuals, right? And it's also going to have some representation of the social networks. So the regressors in a typical social interaction regression are typically just, you know, the individual characteristics, individual attributes. But it's also the case that edges can have attributes. And to give you a simple example, if we think about the social networks in which we all live, on the one hand, there are people that we are very close to, our friends, our family, okay, who are very important to us. And then on the other hand, there are people who are our casual acquaintances, people we know to say hi to, people who we might get together with, you know, once every few months for something, or we talk with on the phone. Maybe they're Facebook friends that we've never even met. Okay. But they're people, you know, that we know. Okay. So these are, and then of course we have everything kind of in between. What I now want to talk about is how these different kinds of links that we might have in social networks can actually be important economically. So I'm going to talk about job search. So the table that you've been staring at while I've been talking is a summary table of the outcome of 4 different studies done by 4 people over a span of 4 author groups over a span of 30 years, okay, which looks at how people found jobs. And in every instance but one in this table, most people, for any job category that is listed here, any of the rows of this table, more people found jobs through relatives or friends, people in their social network, than they did through any other way. Okay. The one counterexample is the accountants in the recent Schultz study, and friends and family were not maximal, but they were still very important. Okay. Studying social networks, if we want to study job search and labor market, seems to be an important thing to do. Okay. Mark Granovetter is a sociologist at Stanford, and back in the late 60s, when he was a graduate student, he had an idea, and it was a really great idea. This paragraph that you're reading is actually about how you might measure his idea. But he said that, you know, the idea I've essentially already expressed, that there are strong ties that we have to our close friends and family, and then there are weak ties that we have to people that we know, okay? Now, there's a lot of things that we can use strong ties for. If I need to borrow money, I'm going to go to a family member, right? Or a close friend. And I'm not going to go to a casual acquaintance, okay? Or if I did, I'd get a very interesting and probably not very useful outcome. On the other hand, let's suppose that I'm looking for a job. If I were to ask my best friend, okay, let's make this very concrete. Suppose that I've decided at my advanced age that I need a new job to finish off my career. Time to get a job in Florida. Okay. So I would go to my close friend, Steve Durlaub, and I would say, do you know of any jobs that are available? But he and I know the same set of people, right? He doesn't really have any information that I don't already have. So he's useful for very many things, but he is not useful for looking for a job, right? On the other hand, if I were to go to some guy that I bumped into at the last ASSA meetings and had a drink with in a bar one night, I might call that person up, right? Or send him an email, right? And that could be very useful because this is a random economist who I don't know very well. That person that probably doesn't share very many social contacts with me. They know stuff that I don't know, okay? So Granovetter's idea was that weak ties might be more useful than strong ties for generating jobs. Or finding job opportunities. So here's a kind of a picture to see why this is true. One hypothesis about the idea of strong ties. Why are strong ties not good for job search? They're not good for job search because a friend of a strong tie, any strong tie to a strong tie of mine is likely also to be connected to me in some way, right? So Stephen and I share a strong tie. Anybody that he is strongly connected to, I'm at least likely to have met, okay? So a lot of the triads, the hypothesis here is that if we look at triads that are strong ties, they're going to be closed. Maybe by a strong tie, maybe by a weak tie, but they're very likely to be closed, okay? And on the other hand, if I go to someone who I only have a weak tie with, random economic historian out there, and I go and I know some economic historians. Let me take a random economic historian who I don't know very well, but I have some connection to them. If that's a weak tie, and I'm likely not to know people that they are strongly tied to, okay? So they're strongly tied to other economic historians. I only know a few economic historians. So, so this is the idea that I want to explore. I want to look at a social network and I want to assume in the social network, I'm going to construct one, and I'm going to assume that any strongly tied triad is in fact closed. And I want to see what the implications for social structure of that, what are those implications? That's what I want to do. So here we have two cliques that are not connected, okay? And now what I'm going to do is I'm going to, oops, that's not what I'm going to do. Here's what I'm going to do. I'm going to draw a link between them. In fact, I'm not just going to draw one link between them. I'm going to draw two links between them. And these two links between them are I put in red. These things are referred to in some parts of the sociology literature as local bridges, right? So a local bridge is an edge whose endpoints have no other friends in common. So if we look at the AB link, all of A's other friends other than B, all of A's other links other than B are to the lower left clique, and all of B's links are to people in the upper right. So the red link connecting A and B is the local bridge, okay? All right, so let's label the edges. And what I've done here is to label the edges in a way that is consistent with my triad hypothesis, that all strongly connected triads are closed. Okay, so if we look at A, okay, and look to the left and look down, those are both left of A A and then down from A is a strongly connected triad. Okay, I'm sorry, is a strongly connected triad. And you'll notice that there is a link between left of A and down from A, so that is closed, okay? If we look at B, the link from B to D, and then we look at the link from D over to the right, that is another strongly connected triad, and I've closed it with a weak link. Okay, but if you examine this graph, you'll see that all strongly connected triads are closed. Now look at our local bridges. My claim is that our local bridges have to be weak. Now, why do they have to be weak? If the AB edge were strong, then A would also have to be connected to D. And if A were strongly connected to D, then D would also have to be connected to the fellow to the left of A, okay? And also to the fellow down from A. The point is that if these two components that have a lot of strong connections within them are connected to each other only by a few local bridges, these local bridges almost surely have to be weak. All right, so this is the role of weak ties in a social network. Weak ties connect very disparate, very distant parts of the social network to each other. And that's why they're valuable in job search. So let me quickly show you an economic model that actually exploits this idea to say something about wages in a labor market, okay? This is a paper. So if you remember that I had this table that I began with, and that table came from a paper by Jim Montgomery. Jim Montgomery is a guy who has a PhD in economics from MIT and was an assistant professor at Northwestern and also was at either LSE or UCL. I don't remember which for a little, which it was. And Jim is now a sociologist in the Department of Sociology at the University of Wisconsin, which is I think by all accounts, a top 5 sociology department. This is a really big career change for Jim. But he's been interested right from the outset in social networks. And I believe this might even have been his thesis, his job market paper, but I'm not sure about that. All right, so let me tell you about his model. So he's going to build a model of job search. All right. And in this model, we're going to assume that people live for 2 periods. Actually, people don't, well, some work, they're going to be in this model 2 periods. Some workers, some workers are going to live for 2 periods, but there's going to be old and young workers, and maybe the young workers live for 2 periods as well, but we don't care about them after period 2. It's going to be a 2-period model. There's an identical number of workers in both periods. Workers vary in their ability. And what's going to happen is we're going to pair workers with firms. Each firm is going to have 1 worker, and high ability workers can produce 1, low ability workers can produce 0. The population is 50-50 each, and workers are observationally indistinguishable at the time they're hired. Okay, so is that clear? Everybody got that? Okay, so now what we're going to do is we're also going to assume that all right, so we're going to assume that profits, well, so how's it going to work out? Profits are for the firm. We're going to assume that the market, we're going to take the numeraire good to be the market price of output, okay? So profits for a firm are going to be employee productivity, either 1 or 0, minus the wage rates that they have to pay to their worker. We're going to assume that there's free entry of firms into this market and that entrepreneurs are risk neutral. Consequently, the equilibrium condition is that expected profits have to be 0 and wage offers are equal to expected productivity or expected value of the worker. All right. Okay. So hope everybody understands that. All right, so if we only had one period, what would happen? Or if we had these 2 periods, we have workers in period 1, and then a new set of workers in period 2. This is why the top bullet is a little misleading. We have workers in period 1, we have workers in period 2, okay? And they're different workers, all right? Just remember that. Everyone's getting paid their expected productivity. Well, you know, half of the workers are high ability, half of the workers are low ability. Expected profitability is equal to 1/2. Expected productivity is equal to 1/2. The wage rate, therefore, is going to equal 1/2. Okay. And the firm will earn either 1/2 or 0, depending upon whether or not they were lucky enough to hire a productive worker. And that's the whole story. So that's a very simple economic story. We can do that one in introductory economics. Now what we're going to do is we're going to introduce social structure. This is the exciting part. Okay. We're going to assume that there are social relationships between period 1 workers and period 2 workers, right? Each worker has, may or may not know, each period 1 worker may or may not know a period 2 worker, okay? The probability that they know a period 2 worker is tau, okay? So the number of workers times tau is the expected number of period 2 workers. Actually, that's not right. So let me not say that. Okay. But let me say that the larger is tau, the more the larger the average, the larger the expected number of workers in period 2 who are tied to somebody in period 1. Okay. It's not linear in tau because it could be that one period 2 worker might know 2 period 1 workers. Okay. But the social network is denser, the larger is tau. That's the point. Everybody got that? That's all I really care about. I don't really care about the probability calculations. Conditional on having a tie to somebody in period 2, that tie is between 2 workers of the same type with probability alpha greater than 1/2. This is a property of social networks, which is known as homophily. The idea that people are tied to people who are like them. Okay, most of us have, most of our friends are similar to us in some way. Right. In fact, it's kind of hard to imagine the opposite. So if you are a productive type in this model, you are more likely than not to be tied to a productive worker. If you are an unproductive type, you are more likely than not to be tied to an unproductive worker. Okay. Given these parameters, assignments are made randomly. I can write down a probability model that does that. Tau, as I said, is a measure of network density, and alpha measures the inbreeding bias, the degree to which social ties are between like people. Okay, so that's our social structure. All right, here's how the 2-period market works. There's an anonymous labor market in period 1. That market clears at some wage rate. Then production takes place, and not only do firms get their output, but they also learn the type of their worker. Okay. Then, independently of all that, social ties are assigned between period 1 workers and period 2 workers. Okay. Now, the old guys retire. The young guys are about to come on the job. Firms are going to consider referrals from their employees. So they're going to decide whether or not to get a referral from their employee to someone their employee knows. And there's going to be a wage rate for referral offers. And because of all the symmetry in this model, all these referral wage rates are going to be the same. Okay. So now what happens next is that these referral offers are transmitted from period one workers to some, to the people that they know, the person that they know. And of course, some workers, period one workers, have no social connections. And so this doesn't even happen at all. Okay. The period two workers who got referral offers decide whether or not to accept the offer or enter the market. An anonymous labor market. And we'll see, by the way, that they will always want to. And then the period two labor market clears at some market wage rate, and then production occurs, and then everybody takes a break. Okay, that's the model. Everybody understand? Okay. So here's what the equilibrium looks like, and I'm not going to spend a lot of time describing this. The Montgomery article is in the reading list, so you can go back and read it. It's a lovely paper. Only firms with productive workers are going to bother to make referral offers. That's not a surprise. Referral wage offers are actually drawn from a distribution which is on an interval where the lower bound is the market to anonymous wage rate and the upper bound is some number that you have to compute. And the reason why this is the case is that there is some monopoly power in the period two labor market because a given period two worker might be assigned to more than one period one worker. So a given period two worker might be receiving multiple job offers. And that gives him a little bit of monopoly power. He's going to take the highest offer, right? And this fact guarantees that there's not a single equilibrating referral wage rate. There's going to be a distribution of referral wage rates. Okay, so let's get on to things that other things. The referral, the anonymous wage rate in the second period is going to be less than 1/2. Okay, why is that true? Well, the people who get referral wage offers are going to take them. Right? Because the referral wage offers are all with probability 1 higher than the anonymous wage offers. Okay. That means that the only people who are going to be in the anonymous labor market are either people who are friends of low productivity workers or people who have no friends. Okay. And the people who are friends with low probability workers are more likely than not to be low probability workers. That's what alpha is doing for us. So consequently, the anonymous market is has a relatively greater number of low productivity workers than high productivity workers. So an anonymous draw from that market has expected productivity less than 1/2. Okay. It's also true that expected profits are greater than 0 in the second period, because with higher probability, well, I'm not going to. This is explained in the paper, and you could actually figure it out from what I've written here, but I don't want to take the time to say it because I'm running out of time, and there's some other things I want to do. All right, so positive profits in the second period. And what's most interesting is that wage rates in the first period, the anonymous first period market, are greater than 1/2. Now, why is that true? I've essentially said this here. When we have no social interaction at all, when tau is 0, or when alpha is equal to 1/2, okay, so that social structure is irrelevant. If there's no relevant social structure, then the only value of a worker in the first period is their first period productivity. Referrals don't mean anything, and that productivity, the expected value of that probability is 1/2. All right, but what happens now if we have social structure? Well, the expected value of the actual value of a high productivity worker is the one that you get that he makes for you in the first period, and also the value of his referral in the second period. And if the second period, if the second period worker is a productivity, a productive worker, you're for sure going to earn positive profits in the second period if you're a firm. And that's more likely than not if you have a high productivity worker. Okay, so the value of a referral from a high productivity worker is positive. Okay, so what is the value of a high productivity worker? It is both the value of his output and the value of his referral. And that collectively is a number greater than 1. Consequently, the expected value of a worker is 1/2 times 0, the probability of it being him being a low probability worker, plus 1/2 times the productive value plus the referral value. And that's going to sum to a number which is greater than 1/2. All right. So that's a description of the equilibrium. What about comparative statics? Okay, well, as the social network either gets denser or more informative, we get the same comparative statics. Okay, the anonymous labor market gets worse in the second period, so expected wages in the anonymous market goes down. Basically, the wage distribution spreads out going up in the upper bound of wages goes up in the second period for referral offers. Profits in the second period goes up. It's also because profits in the second period are going up, referrals are becoming more valuable. And therefore, the first period market wage is going up for the reason that I just described. Okay. So some of this is kind of obvious, right? I mean, that referral should be valuable. This is kind of obvious. What's interesting to me is that the wage rate in the first period of an anonymously chosen worker goes up in a way that it changes in a way that is predictable from the social structure, right? So this is a very clear idea of what social structure can do and how it changes conventional economic reasoning. Okay, are there any questions about this? So I really recommend Montgomery's paper here, 1991 AER. Go look it up. It's an easy read. Okay. So how does this actually work out empirically? I mean, for real. Theory is, fun, but theory is basically, and you're hearing it from a theorist, theory is basically cheap talk. What really matters are the numbers. Okay, so here is a plot from a table from a paper, and I'm going to look and see who the paper is by because I don't remember all of the authors, I'm embarrassed to say. This is a very recent paper. It was written last year. It's an NBER working paper. And the co-authors are Adriana Laris-Mooney, Matthew Miller, Shuyang Sheng, and Veronica Silvero. The title of the paper is Party On, the Labor Market Returns to Social Networks and Socializing. Okay. This set of co-authors took a data set that has data on high school social networks and, among other things, what these people are earning 10 years after graduation. Okay. The reference to the paper so that you can download it is again contained in the on the last, in the reference slides. So what we see in the left-hand table with the data that they looked at is the usual table that we get that talks about the impact of years of schooling on earnings 10 years out. And there's a line for males and there's another line for females. So we see the usual gender gap, okay? But what we're supposed to take away from that picture is that we can see, how wages go up with years of schooling. Now that's not, I mean, I suppose it's interesting, but this is something that, you didn't have to come online today to learn about. Everybody knew about that. What's really interesting is the chart on the right. So what this data set does, or the way it was collected was the following. Students in the first, were initially surveyed in high school. Among other things, they were asked to list 5 friends or up to 5 friends. Okay. we have data. This data set is used a lot for network studies because we have network data here. If I know who you list as friends, and then I know who your friends list as friends and all that, I can construct the social network of your high school. Okay. Once I've done that, I can talk about how big is the component in which you're in. Okay. And that is the number for individuals, which is plotted in the right-hand picture on the horizontal axis. So the horizontal axis is the component size of the social network containing an individual, containing a given individual. It's the component, it's the size of the component in which they sit in high school. And then of course, on the vertical axis again is log earnings. And what we see is that log earnings actually increases with component size. The way that they put this is to say that an increase in wage earnings, this is a quotation, an increase in wage earnings associated with one or more friends is about 2.5%. By comparison, one more year of education is worth, leads to about 10% higher earnings. In other words, 1 year of school is worth 4 friends. Okay, that's the trade-off. So this is a very interesting paper to read. Now you might say, well, gee, how can I make claims like that just by looking at these pictures? Well, of course, this paper was published in the NBER working paper series. They don't make inferences from pictures. There actually is a well-articulated model which controlled for all the things that you would want to control for, so that you can dig out and make causal claims about this coefficient. And here we are back talking about causality once again. Okay. All right. Are there any questions about this? Okay. So now let me ask you a question. I have a couple of, I have a few more slides I could talk about, or I could stop.
I would say keep talking.
Right. Here's actually maybe, here's even a better idea. Instead of voting with your mouth, let's vote with your feet. Okay. I will talk about one more thing. And those of you who would like to stay can. Those of you who don't want to stay will, may leave with no prejudice. Okay. How's that? All right. So let me do that. And I think I should, since I haven't quite talked for my required 3 hours, because I wasted some time getting set up. And, if I talk for 2 hours and 59 minutes, my wage rate is 0. So I better keep going. So I want to talk now about some simple, just going to take you through some simple game theoretic models to show you the variety of things that one can see when one builds game theoretic models of social networks. And I'm going to talk about models of behavior on networks. I am not going to talk about models of network formation. But models of network formation are very important. There's a lot of empirical work, a lot of well, I don't know how much empirical work. There's some empirical work. There's a lot of theoretical econometric work on network formation, all of which is hampered by the fact that we don't have good theoretical models on which to base these econometric models. So again, I think this is an area that's worth thinking about if you want to write a thesis that people will actually pay attention to. Okay. By the way, I think it's really important to write a thesis that people pay attention to for the following reason. Your second job, I hope for all of you, will be a good job, but it probably won't be as good as your first job, which is to say that if we look about changes in jobs over time, more people move down than move up in quality of job. Okay. Now that, by the way, it could be that people are moving to slightly worse jobs because there are other reasons for doing it, like you're closer to family or something like that. But in general, people kind of move down. People are more likely to move down in the rankings rather than up in the rankings. Therefore, you want your first job to be the best possible job. Okay. You should never take a first job so that you can be near your companion, for instance. My wife and I computed. Actually, I realized recently that I've been married for 40 years, and my wife and I have commuted for 15 of those 40 years. And we still raise 2 children who are now in their 30s. And by the way, we were not commuting when we were raising children. Okay, so this did work out. So your first job is really very important because there's more human capital acquisition in your first job than there is in graduate school or anywhere else. Okay, and it basically sets you up for the rest of your career. Now, how do you get a good first job? You write a thesis or have at least a job market paper that is not another Me Too paper. Here is a paper that's motivated by 50 studies that I've read that is marginally different than all of the 50 studies that I've read. That doesn't get you a good job. It gets you a job, but it doesn't get you a good one, right? So I have a friend in the department here who is an assistant professor, and we were talking about what it was like when he was in graduate school, I guess 6 years ago or 5 years ago, and he went to NYU. And he said that in his research group, which was Tom Sargent's macro group, he said people were encouraged to write big papers on big questions. And if you wrote a paper on a small question and presented it in Sargent's research seminar, you were told to throw it away and write something else. Okay, so that's a little extreme, but I'm trying to really push you to say, look for new things to do. Don't do something that is kind of old, kind of new. And what I want to do now is tell you about how to do some new things with tools that you already have. All right. So here is the peer effect model that we started with. Now it turns out that the peer effect model, what I have down below is a quadratic model of the same kind, where the social interaction comes from a strategic complementarity rather than a peer effect. Okay. These models look kind of different, okay, because there's a minus sign in the first one before the beta, and you may remember from game theory that 2 games are said to be strategically equivalent if they have the same player set, if they have the same set of strategies for each player, and even though the payoff functions are different, the best response to any given strategy profile in the first game is the same as the best response for any player to the same strategy profile in the second game. All right. And what you can see from the little calculation that I've done here is that the peer effects game is in fact strategically is in fact best response equivalent to a game with strategic complementarities. So from the best response perspective, which is what we care about when we're doing Nash equilibrium, a peer effects game is a strategic complementarity game, and strategic complementarity games are effectively games that are peer effect games, because although quadratic games with strategic complementarities have Nash equilibrium when that parameter gamma is greater than 1, the equilibria don't make any sense. Okay, and you can actually solve a game yourself with the gamma greater than 1 and see why the solution is weird. To check that out on your own, I'm not going to take the time to do that now. So these are essentially, my point is they're essentially the same idea. And the fact is that that if you read the theorem, and you've read it by now, what I mean by the expression diag of gamma 1 through gamma n, what I mean is a diagonal matrix whose diagonal entries are the gammas, you know, gamma 1 for position 1, 1, gamma 3 for position 3, 3, so on and so forth. And all the off diagonal elements are 0. So if you look at I minus that matrix, that diagonal matrix times A, okay, if that matrix is non-singular, then the strategic complementarity game will have a Nash equilibrium. And pure effects always have a Nash equilibrium because gamma is less, each gamma n is less than 1. And as long as in pure effects games, the row sums of A are equal to 1, the gammas are all less than 1. And it's a fact of linear algebra that I minus diag matrix times A in that case is always invertible. Okay, you can check that out again for yourself. You know, yeah, I'm looking at the right stuff. Okay. There's also an incomplete information version of this game, and I've actually written it out here. I don't want to take the time to talk about it now because I'm really pushing the limit. But I want to say that this is the game that a paper that I referred to previously that I wrote with Stephen and several other co-authors that has appeared in the JPE. This is the game that that paper analyzes. And but you won't find in that paper what I think is the most interesting theoretical finding of that game. And that fact is basically the following. You can find a Nash equilibrium for this game. This game has a lot of macroeconomics in it because you do backward induction and you use the contraction mapping theorem in order to find an equilibrium. And if you took macroeconomics, you may or may not have learned something about GDP. You may or may not have learned something about business cycles, but I know that you did learn dynamic programming. And dynamic programming, it is a best response operator, which turns out to be a contraction mapping, and it's the Banach fixed point theorem that says that there is an optimum for the infinite horizon game, and it's for the infinite horizon problem. And the same idea works in game theory. And here we're just going to do iterated backward induction. You start with the strategy profile. You then apply the best response operator. And then you get a new strategy profile. And then you apply the best response operator again, and you get another strategy profile. And that sequence will converge to the Bayes-Nash equilibrium of this incomplete information game. How is it an incomplete information game? Every player knows his own H, but doesn't know the other H's. All right, but there is a common prior from which the other H's are drawn. I'm assuming that you have studied Bayesian games a lot, but remember very little. But you can go back and kind of check this out, and it'll come back to you. So the cool thing that I want to show you, I'm going to cut right to the chase. I'm describing in these slides, I'm skipping all this iteration business, but let's actually look at what happens when you start doing the iteration. If you start with a strategy, which is everybody is doing the same thing independent of type, the best response, I guess I've given here everybody a common gamma. The best response is for and gamma is less than 1. The best response is to choose 1 minus gamma times your H. All right. Now, suppose that everybody is choosing 1 minus gamma times their H. The best response to that is to do 1 minus gamma times H plus 1 minus gamma times the average of what you think everybody else's H is given your H. Okay, so you're now kind of looking at what you think other people are doing, right? So this is what game theorists call first order knowledge or first order expectations of what others are doing. Now let's look at let's apply this best response operator once again. You have the same two terms that we had before, and we can show that every time we do this best response thing, all we're doing is adding another term onto this infinite series. And because of these gamma squared, it was gamma squared, gamma cubed, this series will converge. Okay, so what is this thing that we're adding on? This is really cool. This term that we're adding on is your expectation given your HN of everybody else's expectation of everybody else's average. Let me say that one more time. It is your expectation of the average of everybody else's expectations of everybody else's average expectations. So that's second order knowledge. What do I know? What do I think that you think that all the other people are doing? And guess what we do at the fourth stage? What do I think that you think that others think about others, right? And so on and so forth. And if you remember something about common knowledge from if you remember rationalizability from game theory, right? This is closely related. And I'm not going to spend time talking about that relationship, but I will say that if you're interested in this, Steve Morris at Princeton has written several papers on this, which are not yet in the references, but should be. So I will put them in the references. I'll put one paper in particular in the references. There's a paper in Review of Economic Studies in the 1990s. He's very interested in this idea between connecting social networks on the one hand with information networks and iterated beliefs on the other hand, and seeing some commonalities amongst them. So I think that this is cool. And this is the only thing that in this talk that I'm doing, because I think it's cool theory, okay, that may or may not be relevant for anybody. But when you do an econometric implementation of this model, this won't happen. All this stuff vanishes if everybody's H is independent of everybody else's H, okay? All these terms just collapse. But in, you know, so if you want to assume that every individual's errors are uncorrelated in this model, which actually has been used as a basis for empirical work, if you want to assume that errors are uncorrelated, you don't have to think about these conditional expectations. But if errors are correlated, then you get this very interesting structure to the distribution of error terms. By the way, all this turns out at the end of the day just to be a big funny constant, but this is the content of the constant. I think it's cool. All right, enough with cool stuff. Let's get on to important stuff. And I'm going to skip that, and I'm going to go to some examples of games. So now what I'm going to do is I'm going to look at games of complete information, which are going to be seeded. It's going to be our basic quadratic game or variations on the quadratic game. Make sure I'm on the right slide here. Okay. By the way, one consequence of all of that stuff that I just talked about, if you go and you read our paper, I don't generally advertise my papers when I talk, but I want to say that if you're interested in doing empirical work in social networks, you're going to come across something called the reflection problem. Okay, and this is the claim that social network regressions are not identified. And if you start reading in the literature, you'll come across this. And I want to say that the paper that introduced this idea was written by a guy named Chuck Mansky. Mansky is perfectly correct. The paper is 100% correct, and it is an extremely special case of social networks. And typically it is the case that social networks are identified. And I have seen a number of job market paper presentations where someone comes into the room and starts talking about the reflexivity problem, or rather the reflection problem in their paper, which is supposed to be an identification problem, and the identification problem doesn't exist. And so they start talking about problems with identification. And I raise my hand and I say, excuse me, but your model is in fact identified. Have you read paper XYZ, which is not by me? I cite another paper. And it's fun to watch the reactions of the speakers. Some people fall apart. Some people say, oh, thank God. Now I don't have to do all this stuff I'm doing. So this is something I think you should be aware of, that the typical social interaction model actually is identified. And so, okay, that's all I have to say about empirical work. So now let's go on to back to the basic model. I now want to go back to complete information, and I want to assume that we are econometricians sitting outside the model. And although every individual knows the H's of everybody else, we, the econometricians, don't know the H's. And so the question that we have is, what can we learn about the H's, and what can we, or actually, I'm going to assume that we know the distribution of the H's, and I'm going to say, what can we learn about beta, the strength of the social interaction? Okay, what do we know? What can we learn from the aggregate statistics? I guess that's generally what I want to question I want to ask. What can we learn from aggregate statistics? From observing people play this game. So if we look at the complete information game, and you do the computations, it turns out that the strategy of any individual is, I guess what I've done here is I've assumed that that everybody is putting equal weights on everybody else in the network. All right. So this is more of a social group. So it's an easier model to understand than having a network with more complicated network structure. This is the completely connected network. Okay. And this is where you should start. There are two places you should start in trying to construct any theoretical network model. One place to start is assuming that your network is a tree. The other place to start is assuming that your network is completely connected. And they kind of span the set of things that can happen. All right. So what's going to happen is we're having everybody average the behavior of everybody else. Therefore, the play of any individual who receives has private type HN is going to be HN plus beta times the average of the distribution divided by 1 plus beta. Okay. And consequently, when we, the econometricians, take a look at this, we see that the expected choice of any individual is equal to the expectation of the private type. Okay. And we also see that the variance of the individual the individual choice is equal to the variance of the population, H, the variance of the distribution from which H is drawn. Does anybody see an error in this slide? The error is it should be divided by 1 plus beta squared, not 1 plus beta, right? If you take a random variable X with distribution sigma squared and you multiply it by a scalar A, right? The variance goes up like A squared, right? So I made a little mistake here. This should be 1 plus beta squared. I am humbled and I will fix this, okay? Because otherwise someone's going to think I'm really stupid. Okay. So here's a different setup. But what I've done in this setup is I kept the same game, okay? But notice that I've changed the way we measure the social interaction. So now instead of looking at the square of the the square of the difference of an individual from the average, we're now looking at the 4th power. So what is the effect of looking at the 4th power? Okay, how does it differ from the square? It lowers the disutility if you're less than 1 away from S bar, and it raises the disutility if you're more than 1 away from S bar. So now it's saying that if you're near enough, the social interaction effect doesn't matter too much. If you're far away, okay, the social interaction effect is becoming really, really big. Okay. And you can compute some things about this. And instead of kind of going through these details, let me show you a picture. So here's a picture where the mean H is equal to 0, but the distribution is asymmetric. Okay, so with probability 6/10, H is -4. With probability 6/10, H is +4. And these are actual computations of the optimal choice of an individual in equilibrium. The purple line is what you should do if you are an H equals 6 type. The bottom line is what you should do. The blue line is what you should do if you're an H equals -4 type. Okay, and the ugly colored line, which it's such an ugly color that it has no name. The color of the line in the middle, I'm sorry, what the line in the middle, the ugly colored line in the middle, I'm focusing on the color because I can't stand it, but I unfortunately couldn't control it. The color of the line in the middle, or the colored line in the middle, describes the average play of the population. And now you can see in this model that the average play of the population actually depends upon beta, whereas it did not depend upon beta in the quadratic model. Okay, Furthermore, what you can see, of course, is that when beta is equal to 0, the optimal choices is that everybody do their own thing. The 6 types choose 6, the 4 types choose 4. I'm sorry, the -4 types choose -4, but they converge together as beta gets very large. And furthermore, because of the nature of the asymmetries, as beta gets very large, average play, and in fact, the play of everybody is going basically negative. Okay. So you can actually write down the first order conditions and set this up in MATLAB or Python. And because you guys took macro, you know how to do all of that. And you can play with this. And I wish we actually did more computation in micro, but we don't. And you can learn something from this about how these social interactions work. So let's actually now kind of go all the way to look at a threshold model. Okay, so here there is no cost to being within one of the average of everybody else. And otherwise you pay a flat cost of a flat disutility of 1. Okay, so this is a model that's a little bit harder to work with, but you can work it out. If you can say some things about it. So there always is an equilibrium, that's clear. If the distribution is symmetric, here's what the equilibrium is going to look like. So let's, and just to make it a little more easy to talk about, let's suppose that H is symmetrically distributed around 0. Okay, then here is what the equilibrium is going to look like. If your H is within the interval plus and minus 1, from -1 to +1, you're going to choose your H because there's no cost to, you're in the region where you don't experience any disutility from deviating from the mean. So you're going to choose your own H. Okay. If your H is very far away from 0, you're going to say it is worth it to bear the disutility of -1 for being different. So I'm going to do my own thing and the hell with everybody else. And again, you're going to set your behavior equal to H. There's going to be a region in between where H is greater than 1, but below some threshold, where you are going to feel the social pressure, okay? But you're not going to want to go all the way down to the mean play, okay? And so what's going to happen there is that those people with H's in that region are going to pile up at +1 if their H's are positive, or -1 if their H's are negative, okay? So as we imagine, for instance, now that we're going to look at people starting from H equals 0 and increasing H. First, we have people doing exactly what their H is. And then we have people, as H goes farther along, we have people who would like to do more, okay, but they can't do more because they have to bear this cost of 1 if they do a little more. So suppose, like, for example, your H is equal to 1 plus, suppose your H is equal to 1.001. Are you really going to do 1.001 and get that -1 utility hit? Or are you going to do 1 and get no utility hit at all, right? So now you're in that threshold region, you've gone up, now you're in this threshold region, and then you're going to get to some point where you're going to say, oh, the heck with this, I'm just going to do what I want to do and go up again, okay? So we can actually compute what that threshold is in the case of some distributions. So I did this for the uniform distribution, where H was uniform on some large enough interval. And it turned out that the threshold the thresholds are ±1 plus the square root of beta. So if you're less than 1, if you're again, so if H is between 0 and 1, you do H. If H is greater than 1 plus the square root of beta, you do H. Okay, and if H is between 1 and 1 plus the square root of beta, you do 1. So that's kind of a complicated model. Now, why is a different model like this important? So there is a paper that was published by Carolyn Hauksbee in the Journal of Economic Literature on the and I think there are some co-authors, and they talk about pure effects in classrooms. And in this paper, the authors give a list of something like 6 or 7 different ways that peer effects might actually work. Okay. You know, it might be, for example, that the best students in a classroom are a role model that everybody else attaches to, right? So in this case, what you really care about is how far away you are from the maximal order statistic of the distribution of outcomes. It might be that the way the peer effect works is that the worst students take up all of the students' time. The best students don't get the attention, or other students don't get the attention that they need. And so therefore the relevant peer effect is driven by the minimal order statistics or some low part of the distribution, okay? Yet another model is the average model that we've been talking about. And then she has several others as well. The point is that every one of these things leads to a different kind of phi function, okay? And this is an area, I think, that has been very under-theorized. What exactly is the way that peer effects work? So if you are an economist with behavioral instincts, this is a great opportunity for behavioral economics. So you can imagine, for example, thinking about different models and read the literature, because there's a large literature on this in Ed Psych. You can read the literature on how peer effects might work and how different kinds of classroom effects might work, and then use that to actually test out different phis, and then look at how this has the kinds of impact this has on the equilibrium educational outcomes. Okay, so there's a great thesis research topic right there. Okay, okay, let's go to one more model. Let's not do, all right, let me just, you can look at this slide on your own, but let me say that what is cool about this model is the model that with the payoff function that I've described, is that you might think that if everybody's all doing the same thing, then peer effect should be really large. But if everybody's really doing all very different things, right? And you know, it's not that everybody's concentrated, but everybody's really spread out, then peer effect should really be small, because the peer isn't, the median or the mean isn't really salient, okay? And so here what I've done is to make the strength of the social interaction decrease with the variance of choice, okay, in a very particular functional form. And I have solved this model, okay? And again, this is a game theory classroom exercise for bright undergrads, so it's something you all can do. And what you discover is that as beta increases, the concentration increases. So, which is to say that the variance of play shrinks as beta increases, having fixed the variance of the individual H's at 1, okay? So if I fix the distribution, the variance of the type distribution, and remember, this is a complete information game. The person who doesn't know the type, doesn't know the actual types, is the econometrician. If we fix the variance of the type distribution, so we're actually looking at samples of lots and lots of different games, okay? The variance of actual play decreases with the strength of the social interaction effect. So this is another example of how we can use variance as part of a strategy to help us identify social interaction effects, which is something that we talked about at the very beginning of the hour. And the last model that I want to talk about, this is an important model. Social interaction models, this is, I'm going to stop at the end of like 1 slide or 2 slides, honestly, really am. Okay, so anytime you go into an empirical talk on where someone says, here's a social network, now I'm estimating behavior on this network, someone is going to say, oh, this is all crazy because the social network is endogenous. Okay, so if you're looking for a job, you construct a new social network every time you look for a job, okay? And, or if you are, you know, looking to find a good college a good university to send your, or that's not a good example, because you won't have a choice in where your children go to school. Okay, they're going to make their choice, and you're just going to have to live with it. That's the real truth. But if you are looking, for example, which preschool to put your first child in, you're going to construct a social network to do that. And then when your second kid comes along, you're going to construct a completely different social network to do that. Now that's obviously crazy, okay? But it's certainly the case that you are going to start trying to expand your social network by asking friends of friends that you might not know, right? Calling up people to get some information when you're looking for a school. So to some degree, the social network is endogenous. And so I want to talk about a kind of network endogeneity that we can actually talk about here. And you've already read the slide, so you can see what I'm talking about. I'm going to suppose that people sort themselves into two groups. So I don't know what it was like for most of you, but when I was in high school, there were cliques of people that hung out together. And if you were not hanging out with the people in a certain clique, you really didn't care what those people were about, right? So I know it's hard to believe, but I actually was not an athlete. Okay. And since I was not an athlete, I was really not very influenced by the athletes. Okay. I was into music. And so I hung out with the music types, right? And they were my peers, and they're the people that I responded to. And then there were the people who spent all their time acting out in class and being in trouble and kind of, skipping classes and smoking. And they weren't influenced by anybody else, right? Except themselves. So we know this kind of social structure. This is the kind of social structure that I'm going to talk about, that people were going to have our basic quadratic peer effects model, but people are going to endogenously break themselves into groups. Okay. And then respond to the play only within their group and not with respect to the other group. So we can think about this as a two-stage game. In stage one, people choose a group. And in stage two, okay, they then react to the play. We have the usual Nash equilibrium that we've been doing, but people are reacting only to the play of people within their group. Okay. So is that story clear? Right. So now, how are we going to solve this? We're going to solve this by backward induction. We're going to say for any given division of people into groups, what does the Nash equilibrium of the two groups look like? Okay. Within the two groups, the second stage Nash equilibrium within the two groups look like, and then we'll say, well, does anybody now want to switch groups? Okay. And when we have a Nash equilibrium within each group, and the groups are such that nobody wants to move, that's a Nash equilibrium for the two-stage game. Okay. So the first thing that should be obvious is that people are going to sort themselves according to, in equilibrium, people will sort themselves according to H. Why is this going to be true? Imagine that we have two groups. One group has a high, so I guess there's the completely degenerate case that basically doesn't occur unless the parameters are set up the right way, where the two groups have equal means. But except for that, okay, the two, divide the population any way you want into two groups. The two groups will have different mean plays in equilibrium. Now, if you are now let's suppose that we have some high H people in the low mean group. They're going to say, hey, I'm going to be better off if I go up to the high, up to the high mean group. So they're going to want to switch. And if we have low H people in the high mean group, they also are going to want to dive down into the low mean group. Okay, so that can't be equilibrium. So the only equilibrium can be where we have low people in the low group and high H people in the high group. And then what we have to do is we have to just find the dividing point. So that now becomes an easy problem to solve. Okay, we just want to find, we want to imagine that there's a parameter H star, and then we compute the mean equilibrium for people above H star and the mean equilibrium for people below H star. And now we look at which group H star wants to be, and we just start moving up H star until we get to the point where person H star is indifferent between being in the high group and being in the low group. Okay, and that's the equilibrium. Okay, and I have actually done that. and I've already told you essentially, so when you solve this model out in the, and there's some points on the slide that you can read up on. But if you solve this model out, you'll find that the separating H star is independent of beta, is independent of the social choice effect, of the power, the magnitude of the social choice effect. And you can actually compute it for different distributions of H, and I did that. So a uniform distribution, not surprisingly, H star equals 1/2. Okay, so now what I did next was I took a distribution which was skewed to the left. This is actually the wrong thing to do because we know that distributions of ability skew to the right. But I don't know why I don't know why I did this. And unfortunately, I did this in Mathematica and I no longer have a Mathematica license. So I couldn't recompute it for this talk. But in the example that we have, what's happening is that the density gets thicker as you go up to 1, right? What you see is that there is a unique equilibrium, again, which separates at this number, which is greater than 1/2, right? And by the way, I don't remember, can I do this quickly? Suppose I want to integrate x to the power 4 times 3. Right. So the mean is 3/4. Okay. You can see that the separation is just a bit below the mean. Okay. I hope I did that right. You can do this on a piece of paper. Compute the mean of 3x squared. Okay. If I had done this in a more natural way, I would have chosen my density to be something like 1 minus 3x squared, or better yet, more likely 3 times 1 minus x squared. That's what it would have been. 3 times 1 minus x squared. And then the distribution kind of skews to the right, the way that we think ability distributions do. And H star and the mean would have been 1/4, and H star would be at 1 minus this 0.69 number, right? Which is a bit bigger than the mean. So you can compute with you can play with a number of these different things. And I want to show you what I wanted to show you in this last slide was that we can actually talk about endogeneity, at least in some settings. And you can see that endogeneity has an impact. If you can build a model like this, even a toy model like this, then it's possible to estimate a much richer structural model. You could actually build a structural model that you could actually take to data. And it's realistic to use these kinds of models in doing empirical work. Right. And that's the point that I want to leave with you, that you can, I've just shown you a bunch of little toy things, but you can actually use these insights to do something interesting empirically. So I hope that some of you do this in your theses. And I want you, if you do, I hope you'll send me the papers and you'll send me a little note saying, I did this course and I tried to do something cool, something interesting, and here's my paper, and let me know. And in particular, I hope that I would really be excited if you pick up on any of the suggestions that I made and see if they lead anywhere. But I want you to be careful because I always tend to tell students to do too much. And so they work on that for, a year or so, and then they go do something else. None of those suggestions have I shared with students at Cornell. Try some of these ideas out and do let me know if you find anything interesting. And thank you very much for all of your time.
Thank you. That was really interesting. Thanks a lot.